When you hear, "the universe is expanding," what picture pops into your head? For most of us, it's a ball of galaxies exploding outwards, a cosmic firework pushing into a huge, black, silent nothingness. It's a powerful image. It makes perfect sense. And it's completely wrong. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. That picture is a trick your brain is playing on you. Our minds evolved to understand rooms, fields, and horizons, things we can walk to. They didn't evolve to grasp the boundless, stretching fabric of spacetime. The reality of our cosmos is far stranger, more elegant, and more wonderful than that simple picture. To get what the universe is really doing, we have to forget about an edge. We need to stop asking what it's expanding into. The answer isn't out there. It's woven into the very nature of reality itself. There's a crisis in cosmology, but it isn't happening in the darkness between stars. The crisis is in our heads. It's the battle between our gut feelings and a century of mind-boggling evidence. The idea of something getting bigger, without getting bigger into anything, feels like a paradox. It's like asking what's north of the North Pole. The question itself is broken. But this isn't just a word game. The discovery that space is expanding completely reshaped our place in the universe. It took us from thinking we lived in a cozy, static, eternal cosmos to knowing we live in a dynamic one with a definite beginning. To really wrap our heads around this, we can't just skip to the answer. We have to follow the clues, just like the great astronomers of the past did. We have to become cosmic detectives. The detective story, Echoes from the Abyss. Our story starts not with a bang, but with a whisper, a subtle shift in the color of light from fuzzy blobs in the night sky. In the early 20th century, astronomers argued about what these spiral nebulae were. Were they gas clouds in our own Milky Way? Or were they island universes, entire galaxies floating in an abyss far beyond our own? The first clue was uncovered by a quiet, meticulous astronomer at the Lowell Observatory named Vesto Slipher. Starting in 1912, he took on a ridiculously hard task. Night after freezing night, he used a spectroscope to split the faint light from these nebulae into a rainbow of colors. He was hunting for spectral lines. Think of them as the unique color barcodes for elements like hydrogen and helium. But these barcodes weren't always where they should be. Just like the pitch of an ambulance siren drops as it speeds away, the light from an object moving away from us gets stretched. The light waves get longer, shifting them toward the red end of the spectrum. We call it redshift. Slipher pointed his telescope at the Andromeda Nebula and found its light was actually blue shifted. It was hurtling toward us. But as he looked at other nebulae, a shocking pattern emerged. Almost all of them were redshifted. And not just a little. Some were flying away at thousands of kilometers per second. He had found the first hint that the universe wasn't static. It was in constant motion. Slipher knew they were moving, but he didn't know how far away they were. That brings us to our second, more famous detective, Edwin Hubble. Working with the most powerful telescope in the world at the time, the 100-inch Hooker telescope in California, Hubble was about to blow the case wide open. He used a breakthrough from another brilliant astronomer, Henrietta Leavitt. She had discovered that a special type of star, a Cepheid variable, pulses at a rate tied directly to its true brightness. They're like cosmic light bulbs of a known wattage. By comparing how bright a Cepheid looks to how bright you know it really is, you can calculate its distance. In 1924, Hubble found a Cepheid in Andromeda. His math placed it nearly 1,000,000 light-years away, proving it was a separate galaxy, an island universe. In a single moment, the known universe became unimaginably bigger. But Hubble didn't stop. He combined his distances with Slipher's redshift speeds. When he plotted the data on a graph, the relationship was breathtaking. The farther away a galaxy was, the faster it was moving away from us. This wasn't random. A galaxy twice as far away was receding twice as fast. 10 times farther, 10 times faster. This became known as Hubble's law. The evidence was clear. The entire universe was expanding. This discovery, however, leads directly to that intuitive trap. If everything is flying apart, it must have exploded from a single point into a pre-existing, empty void, right? This is our earthly intuition failing us. Because the evidence tells a different story. There is no center to this expansion. And if there's no center, the whole idea of an explosion in space falls apart. To see why, we need a better analogy. We need to bake some bread. The analogy: breaking your brain with bread and balloons. The detective work of Slipher and Hubble showed us galaxies are rushing away from each other. But to understand how, we need a new way of thinking, not of things moving through space, but of space itself expanding. Enter the raisin bread. Imagine a lump of unbaked dough with raisins mixed all through it. You pop it in the oven. As the dough bakes, it rises and expands. Now, let's pick one raisin to be our home, the Milky Way. As the dough swells, what does our raisin see? Every other raisin moving away from it. A nearby raisin that was an inch away is now 2 inches away. A more distant raisin that was 4 inches away is now 8 inches away. The farther the raisin, the faster it seems to recede. This is a perfect picture of Hubble's law. But here's the crucial part. Are the raisins actually moving through the dough? No. They're just being carried along as the dough itself expands. The space between the raisins is what's growing. And now for the mind bender. Pick any other raisin. From its perspective, it sees the exact same thing. All other raisins are moving away from it. Every raisin can claim to be the center, which really means that no center exists at all. This is what we see in our universe. It's not that galaxies are flying away from a single point. It's that the fabric of spacetime, the dough, is stretching and carrying the galaxies with it. This is called metric expansion. The raisin bread is a great start, but the loaf has a crust. Our brains immediately ask, what's outside the bread? So, let's upgrade our analogy to something without an edge: a balloon. Imagine drawing a bunch of dots on a deflated balloon. These dots are galaxies. Now, start blowing it up. The dots all move away from each other. A dot on the opposite side moves away faster than a dot right next to it. Hubble's law still works. The dots aren't sliding on the rubber. The two-dimensional space of the balloon's surface is what's stretching. Now, where is the center of this expansion? It's inside the balloon, in the air, which is not part of the 2D surface universe. Where is the edge of the surface? There isn't one. A 2D creature on one of those dots could walk forever and never fall off. They'd just end up back where they started. The surface is a finite space with no boundary. This is the key. Our universe is thought to be like this, but in more dimensions. The expansion isn't our 3D universe pushing into a 4D void. The 3 dimensions we inhabit are stretching intrinsically. The question, what is the universe expanding into, assumes there is an outside. The balloon shows us how a system can be self-contained. It doesn't need an outside to expand. It just expands. The revelation: space, time, and the shape of reality. With our brains rewired by bread and balloons, we can face the reality they represent. The idea that space is a dynamic thing comes directly from Albert Einstein. In 1915, his theory of general relativity showed that gravity isn't a force, but the result of mass and energy warping spacetime. Think of a bowling ball on a trampoline. A marble rolled nearby will curve towards it. But when Einstein applied his equations to the whole universe, they said it should be collapsing under its own gravity. Since everyone at the time believed the universe was static and eternal, he added a fudge factor. He called the cosmological constant a kind of anti-gravity to hold everything in place. A decade later, Hubble announced the expansion. Einstein realized his original math had been right all along. He had missed the chance to predict the expansion and called the constant his biggest blunder. As we'll see, that blunder was about to make a shocking comeback. The math behind this expansion shows that the metric, the ruler of space, is changing everywhere. Space itself is growing. So, the direct answer to our question is: the universe is not expanding into anything. It's expanding into itself. Space is not a container. It's a self-contained system expanding intrinsically. Asking what's beyond the universe is like asking what's north of the North Pole. In a spatial sense, there is no beyond. This leads to the question of the universe's overall shape. General relativity allows for three possibilities, depending on its total density of matter and energy. 1. Closed. Like a sphere. Finite, but with no edge. In this scenario, expansion would eventually reverse into a big crunch. 2. Open. Like a saddle. Infinite and expanding forever. 3. Flat. Like an infinite sheet of paper. Infinite and also expanding forever, though the expansion would slow down. To figure out which we live in, we look at the cosmic microwave background, CMB, the afterglow of the Big Bang. It has tiny temperature fluctuations, hot and cold spots whose original size we know. By measuring how big these spots appear to us now, across 13.8 billion years of expansion, we can measure the geometry of space. It's like drawing a giant triangle across the cosmos. The results from satellites like WMAP and Planck were astonishing. To the best of our ability to measure, the universe is perfectly flat. For years, this suggested our universe was infinite and would expand forever, albeit slowing down over time. But in the late 1990s, astronomers measuring that slowdown found the biggest shock in modern cosmology. The expansion isn't slowing down at all. It's speeding up. This journey into the nature of space is just one piece of the cosmic puzzle. The discovery that the expansion is accelerating introduced a new, mysterious player onto the cosmic stage: dark energy. If you want to understand what this bizarre, universe-stretching force is, and how it will determine the ultimate fate of everything, be sure to subscribe and hit the bell, because that's where we're going next. Your support helps us tackle these mind-bending questions, and we'd love to have you with us as we explore the deepest mysteries of the cosmos. The deeper dive, horizons, acceleration, and a cosmic twist. Okay, so space itself is stretching. But that idea opens up a whole new can of worms, forcing us to think about the limits of our vision, the engine driving the expansion, and the ultimate fate of everything. First, let's talk about the observable universe. The universe is about 13.8 billion years old. Since light takes time to travel, we can only see objects whose light has had enough time to reach us. This creates a bubble of observation around us, with a boundary not in space, but in asterisk time. An alien astronomer in a distant galaxy has their own observable bubble, overlapping with ours but seeing parts of the cosmos we can't. This proves again, there's no special center. But the stretching of space adds a terrifying twist. The expansion of space itself has no speed limit. Far enough away, the space between us and a distant galaxy can be stretching faster than the speed of light. This doesn't break any rules, nothing is moving through space that fast. But it means that light from those galaxies is like a runner on a treadmill that's pulling them backward faster than they can run. They are beyond our cosmic horizon, their light never to reach us. For over 2 decades, it seemed this process was getting worse. In 1998, astronomers discovered the expansion is accelerating. The culprit was named dark energy, an unknown force that seems to be a property of space itself, pushing everything apart. This discovery won a Nobel Prize, and for years, it painted a lonely picture for our future: a Big Rip, or heat death, where all other galaxies would accelerate away beyond our view, leaving our own galaxy alone in an empty void. But the universe might have another surprise for us. For a long time, the leading theory assumed that dark energy was a constant, never changing. However, recent data in 2026 is challenging everything we thought we knew. An analysis from researchers at Cornell suggests dark energy may not be constant at all. In fact, it might be weakening. This new evidence hints at a shocking future. The model suggests dark energy could peak in about 11 billion years, and as it fades, gravity would once again become the dominant force on a cosmic scale. Instead of ripping apart, the expansion could slow, halt, and then reverse. The universe might be destined not for a cold, empty death, but for a fiery, big crunch, about 20 billion years from now. This whole debate is complicated by a famous problem called the Hubble tension. Measurements of the expansion rate today using local methods, like supernovae, give a value of about 73. But predictions based on the early universe, via the CMB, give a value of 67. They are both precise, and they don't agree. This tension could be a clue that we're missing a piece of the puzzle. As of 2026, new methods using gravitational waves are offering a fresh perspective, hopefully getting us closer to a final answer. The new perspective. So, let's go back to that image of a bomb exploding in a room. It feels completely wrong now, doesn't it? We've replaced it with something far grander and stranger. The universe is not an explosion in a room. It is the room itself, stretching in all directions, with no center and no edge. The galaxies are just passive riders on a current of expanding spacetime. Our journey has shown us that our intuition, built for life on Earth, breaks down completely when faced with the cosmos. To understand it, we have to let go of our basic assumptions and trust the faint, ancient light that has traveled for eons to tell us its story. The question was never, what is the universe expanding into? The real question was, what is the nature of space itself? The answer is that space is not nothing. It is a dynamic, physical, stretching fabric that forms the very stage of our reality. And now, the final chapter of that story is up for grabs. For years, the evidence pointed toward a lonely, dark future. Today, the story is more thrilling than ever, with a cosmic tug-of-war between dark energy and gravity whose winner is still unknown. We are living in a singular moment, a time where we can still see the distant galaxies and have the tools to decode their secrets, perhaps just in time to find out how it all ends. Why everything you know about universal expansion is wrong. When we look up at the night sky, we see galaxies hurtling away from us in every direction. It feels like we're watching the aftermath of a colossal explosion, a cosmic firework show scattering embers across an infinite night. This picture, of galaxies flying through space, is powerful. It's simple. And for most of us, it's how we imagine the expanding universe. But this very simple, obvious idea leads to a question that seems to have no answer. What is the universe expanding into? If it's an explosion, there has to be an empty room for it to fill, right? A void beyond the last frontier of matter. For decades, this question has felt like a logical trap, a paradox that seems to show a huge flaw in how we see the cosmos. But here's the secret: it's the wrong question. And it's the wrong question because we've been focused on the wrong thing. The galaxies aren't the main characters in this story. They're just along for the ride. The true star of the show, the thing that's actually doing something, is space itself. The grand deception. Our intuitive, explosive universe. The mental picture most of us have is shaped by everything we've ever seen. We see a firework burst, and shrapnel flies outwards through the air. We see a bomb go off, and debris is launched through a pre-existing space, away from a central point. So, we apply that same logic to the cosmos. The Big Bang, in this view, was the ultimate explosion. A single, infinitely dense point blew up, flinging all the future stars and galaxies out into a huge, pre-existing emptiness. This model just feels right. It explains the main thing we observe. Galaxies are moving away from us. The explosion story gives us a neat, tidy explanation. It gives us a clear cause and effect. The bang happened over there, and now everything is moving out here. It even seems to explain why more distant galaxies are speeding away faster. Of course, the fastest moving bits from an explosion would travel the farthest in the same amount of time. This picture of the universe is simple, it's elegant, and it's almost completely wrong. The explosion in space model isn't just a casual mix-up. It's a way of thinking that creates a whole mess of unanswerable questions. If it was an explosion, where's the center? Where is that one spot where it all started? Our telescopes show that, on the biggest scales, the universe looks pretty much the same in every direction. There's no special point in the sky we can point to and say, that's the origin. Instead, it looks like we're at the center of this cosmic stampede, a conclusion that feels both arrogant and deeply unlikely. And then there's the biggest phantom of them all, the outside. An explosion expands into the space around it. So, if the universe is expanding like an explosion, it must be expanding into something. This something would be a void, an emptiness that exists beyond the edge of our universe. But by definition, the universe is everything that exists. So how can there be an outside to everything? It's a logical contradiction, a snake eating its own tail. You can't have space outside of the container of all space. This is the dead end the explosion model leads us to. It forces us to ask a question that makes no sense. The question, what is the universe expanding into, is really just a symptom of a flawed starting point. To find the right answer, we have to throw out our familiar idea of an explosion and go back to the discovery that first pointed us down this road. A universe in motion, the first clues. Our journey to figuring this all out begins not with a bang, but with a whisper of light. In the early 1900s, before we even knew other galaxies existed, astronomers were staring at these strange, faint smudges of light in their telescopes they called spiral nebulae. One of them, Vesto Slipher, started a careful study of these nebulae back in 1912. Using a technique called spectroscopy, he split their light into a rainbow of colors, creating a spectrum. In that spectrum, he was looking for dark lines, absorption lines, which are like fingerprints for the chemical elements in the nebula. He found them, but with a weird twist. For almost every nebula he looked at, those lines were not where they were supposed to be. They were all shifted toward the red end of the spectrum. Slipher and his colleagues figured this must be the good old Doppler effect. We hear the Doppler effect every day with sound. An ambulance siren sounds high-pitched as it comes toward you and low-pitched as it moves away. The same thing happens with light. If an object is moving toward you, its light waves get squished, shifting its spectrum toward blue, a blue shift. If it's moving away, the light waves get stretched, shifting the spectrum toward red, a redshift. Slipher's observations seemed to show that nearly all of these spiral nebulae were hurtling away from us at incredible speeds. But this was just a pile of data points without the big picture. At the time, everyone thought the Milky Way was the entire universe, and these nebulae were just gas clouds inside it. That all changed thanks to the groundbreaking work of Edwin Hubble. Working at the Mount Wilson Observatory in the 1920s, Hubble pointed the most powerful telescope in the world at the Andromeda Nebula. He was looking for a special kind of star called a Cepheid variable. Thanks to the work of another brilliant astronomer, Henrietta Swan-Leavitt, it was known that a Cepheid's pulse rate is directly tied to its true brightness. By timing its blinks, you can figure out how bright it really is. And by comparing its true brightness to how dim it looks from Earth, you can calculate its distance. When Hubble found a Cepheid in Andromeda and did the math, the result was staggering. Over 900,000 light-years away. This was far, far outside the known limits of the Milky Way. In a single moment, Hubble proved that the spiral nebulae weren't clouds at all. They were entire galaxies, island universes, just like our own. Suddenly, the cosmos was mind-bogglingly huge. But Hubble didn't stop. He and his assistant, Milton Humason, measured the distances to dozens more of these new galaxies. Then they measured their redshifts, just like Slipher had. When they plotted the data distance on one axis and speed on the other, a crystal-clear pattern emerged. With just a few exceptions, every galaxy was moving away from us. And the farther away a galaxy was, the faster it was moving. This relationship, known as Hubble's law, was announced in 1929. It was the first solid, observational proof that our universe wasn't just sitting there, it was growing. The explosion model seemed confirmed. But a deeper truth was already waiting in the wings, hidden in equations published more than a decade earlier. The main character, the fabric of spacetime. To really get what's happening, we have to rewind to 1915, to Albert Einstein and his theory of general relativity. General relativity completely rewrote our understanding of gravity. For Newton, gravity was a mysterious force pulling two objects together. Einstein said something far weirder. Gravity isn't a force at all. It's what happens when mass and energy warp and curve the very fabric of reality, a four-dimensional thing called spacetime. Think of it like this. Place a heavy bowling ball on a stretched-out rubber sheet. The ball makes a dent, a curve in the sheet. Now, if you roll a marble nearby, it doesn't get pulled toward the bowling ball. It just follows the curve in the sheet that the ball made. That's gravity. Things moving along the curves in spacetime created by other things. When Einstein first applied his equations to the whole universe, he was shocked by the result. They predicted that the universe couldn't be static. The combined gravity of everything should make it all collapse. This flew in the face of the belief in a steady, eternal cosmos. To fix it, Einstein added a fudge factor, the cosmological constant, to act as a repulsive force and hold the universe still. But other scientists, like Alexander Friedmann and Georges Lemaitre, took Einstein's original equations more literally. They showed that the theory naturally described a dynamic universe, one that was either expanding or contracting. So when Hubble's discovery was announced in 1929, Lemaitre instantly connected the dots. Hubble's data was the real-world proof of what the theory had been saying all along. The universe was expanding. Einstein later called his cosmological constant the biggest blunder of his life. And here is the crucial, mind-bending part that comes from general relativity. The expansion the theory predicted wasn't about galaxies flying through space. It was about space itself expanding. This gives us a whole new way to think about redshift. The redshift Hubble saw wasn't mainly a Doppler shift. It was something else we now call cosmological redshift. A Doppler shift happens when something moves through a static space. But with cosmological redshift, the galaxies aren't really flying away from us at all. Imagine a photon of light leaves a distant galaxy and begins a billion-year journey to us. In the time it's traveling, the space between us and that galaxy expands. It stretches. And as space itself stretches, the light wave traveling through it gets stretched out, too. Its wavelength gets longer, shifting it toward the red end of the spectrum. This is why Hubble's law works. More distant galaxies have higher redshifts not because they're flying faster, but because there is more space between us and them, and that greater amount of space has had more time to expand, stretching the light more severely during its long trip. A better analogy than an explosion is a loaf of raisin bread dough rising in an oven. Pick any raisin. As the dough expands, every other raisin moves away from it. The raisins aren't moving through the dough. They're being carried along by the dough. A raisin twice as far away moves away twice as fast, because there's twice as much expanding dough between them. And from the perspective of any single raisin, it looks like it's the center of the expansion. This is the fundamental shift. The galaxies are just markers, like raisins. The main character is the dough spacetime itself. It isn't expanding into anything. The distance between any 2 points within it is just increasing. This also solves another problem, the cosmic speed limit. Special relativity says nothing can travel through space faster than light. But this isn't motion through space. It's the expansion of space. So, for two very distant galaxies, the space between them can expand so fast that they fly away from each other at faster than light speeds. No laws are broken, because nothing is locally breaking the speed limit. The cosmic crime scene, the smoking guns. Hubble's law was the first clue, but to prove that the universe was born hot and dense and has been expanding ever since, scientists needed more evidence. They needed smoking guns. And they found them, first in the faint glow of the universe's oldest light, and second, in the chemical recipe of the cosmos itself. The first piece of evidence is the cosmic microwave background, or CMB. If the universe started in an incredibly hot, dense state, then in its first moments, it would have been a scorching, opaque plasma. Light photons were trapped, constantly bouncing off electrons and protons like pinballs. The universe was a glowing fog. But, the theory predicted that as the universe expanded, it would cool. About 380,000 years after the Big Bang, it would have cooled to about 3,000 Kelvin. At this point, electrons and protons could finally stick together to form neutral hydrogen atoms. With the electrons now locked up, the universe suddenly became transparent. The light that had been trapped in the fog was finally set free. That light, the very first to travel freely, is what we now see as the cosmic microwave background. As the universe has continued to expand for the last 13.8 billion years, those ancient light waves have been stretched cosmologically redshifted from visible light all the way down to microwaves. In 1965, two radio astronomers, Arno Penzias and Robert Wilson, stumbled upon this radiation by accident. They found a faint, persistent hiss in their radio antenna, coming from every direction, day and night. It wasn't from a star or a galaxy. It was a uniform glow filling all of space. They had found the afterglow of the Big Bang. The CMB is a baby picture of the universe, and it's a perfect match for a universe whose very fabric has been stretching for billions of years. The second piece of evidence is Big Bang nucleosynthesis. In the first few minutes, the universe was hot and dense enough to act as a giant nuclear reactor. The conditions were so extreme that protons and neutrons fused together to form the nuclei of the lightest elements. The models predict that this cosmic alchemy should have created a universe made of roughly 75% hydrogen, about 25% helium, and tiny traces of a few other light elements. This is a testable prediction. Astronomers can look at the most ancient gas clouds and stars places that are chemically pristine. When they measure the composition of this primordial gas, they find that the amounts of hydrogen and helium match the predictions of Big Bang nucleosynthesis with stunning accuracy. The numbers only work if the universe started incredibly hot and dense and then expanded and cooled at a very specific rate. If it had expanded too fast, there wouldn't have been time to make helium. Too slow, and everything would have fused into heavier stuff. It's another perfect fingerprint left behind by an expanding universe. The aha moment. Solving the impossible puzzle. So, with this new picture in our heads that space itself is the main character, stretching and carrying galaxies along with it, we can finally go back to that first, nagging question. What is the universe expanding into? And now, the answer becomes obvious. The question doesn't make any sense. The question assumes there's an outside for the universe to fill, an empty stage waiting for the show. But that idea is a leftover from the broken explosion model. In the world of general relativity, the universe isn't an object expanding inside a larger space. The universe is the space. There is no outside, because the universe contains all of space and all of time. It isn't expanding into anything, it is simply expanding. More space is coming into existence everywhere, between everything. This is where the balloon analogy helps, but you have to be careful. Imagine you are a two-dimensional bug living on the surface of a balloon that's being inflated. As it expands, you see all the other dots on the surface moving away from you. You can walk in any direction and you'll never find an edge. Your entire universe is the curved surface of that balloon. Now, we, as three-dimensional beings, can see the balloon as expanding into the room. This is where the analogy gets tricky. For our universe, there is no higher dimensional room that we know of. The expansion is just a property of spacetime itself. This model also perfectly solves the center of the universe problem. In a bomb blast, there's a clear center. But on the surface of our expanding balloon, is there a center? Nope. Every point is the same as any other. Any dot you pick can see all the other dots moving away from it. This is exactly what we see. An observer in any distant galaxy would see the exact same thing we do. All other galaxies, including our own, moving away from them. So the grand, aha moment is this. The impossible question came from a bad mental picture. By replacing the image of an explosion in space with the mind-bending but more accurate image of an expansion asterisk of space, the paradox just disappears. This shift in perspective is one of the most profound in the history of science. It changes everything. If you find this journey into the true nature of the cosmos as fascinating as I do, consider subscribing. It really helps the channel and ensures you won't miss our next deep dive into the universe's biggest mysteries. The local rebellion, when gravity fights back. So if all of space is expanding, a pretty good question comes to mind. How can anything ever come together? How do stars and planets even form? And how is it possible for entire galaxies to collide? Because we know for a fact that they do. Our own Milky Way is on a collision course with our nearest big neighbor, the Andromeda Galaxy. Andromeda isn't moving away from us. It's hurtling toward us at about 110 kilometers per second. According to our best estimates, in about 4-5 billion years, our two galaxies will start a spectacular, chaotic dance, eventually merging into one giant galaxy some have nicknamed Milkdromeda. This seems like a flat-out contradiction. How can we be heading for a crash if the very space between us and Andromeda is supposed to be expanding? The answer is a cosmic tug-of-war. Cosmic expansion isn't the only game in town. Gravity is still a major player. The universe is a battleground between space wanting to expand and matter wanting to pull itself together. Who wins depends entirely on scale. On the biggest cosmic scales, the enormous voids between galaxy superclusters, expansion wins, no contest. The gravitational pull between these distant clusters is way too weak to overcome the stretch of all that space. But on smaller, local scales, gravity is king. The space between the Milky Way and Andromeda is expanding, but the gravitational pull between our two massive galaxies is so strong that it completely overpowers that expansion. They're being pulled together far more powerfully than the space between them is pushing them apart. This is true for anything that's gravitationally bound. The expansion of space isn't tearing you apart because the forces holding your atoms together are trillions of times stronger. It's not pulling the Earth away from the Sun, because our solar system is gravitationally bound. And our local group of galaxies, the Milky Way, Andromeda, and a few dozen smaller ones, is also a gravitationally bound system. The fact that galaxies can collide doesn't contradict cosmic expansion. It beautifully demonstrates that different forces rule on different scales. The modern crisis, the expansion we can't explain. Just when we got comfortable with this new, elegant picture, modern cosmology threw us a curveball. The story, it turns out, is not over. In fact, we might be on the edge of another revolution, because right now, there's a crisis in cosmology. The crisis is all about one number: the Hubble constant, which tells us how fast the universe is expanding. For decades, we've been trying to nail down its exact value. The problem is, depending on how we measure it, we get two different answers. One method looks at the late universe, close to us in time. Astronomers use things like Cepheid variable stars and specific kinds of supernovas to measure the expansion rate directly. This method gives a value of around 73 km per second per megaparsec. The other method looks at the early universe, using the detailed maps of the cosmic microwave background and our laws of physics to predict what the expansion rate should be today. This method gives a value of around 67. These measurements are both incredibly precise, and their margins of error don't overlap. They're telling us two different things. It's a huge problem. Either one or both of the measurements are wrong in a way we don't understand, or our fundamental model of the universe is missing a key ingredient. This Hubble tension is a thrilling sign that our cosmic story is still unfolding, and there might be brand new physics waiting to be found. Our view of the universe has been completely transformed. We started with a simple idea of an explosion, galaxies flying like shrapnel through a static void. That picture led us to a dead end, with impossible questions about a center and an outside that can't exist. The real revolution came when we realized the galaxies aren't the stars of the show. The protagonist of this cosmic drama is spacetime itself. It's an active, dynamic thing that's stretching and carrying everything along with it. This shift in perspective solves the paradoxes. There is no center, because the expansion is happening everywhere. There is no outside, because space is creating more of itself as it goes. And yet, the Hubble tension shows us that our story is far from over. There are fundamental things about this expansion we still don't understand. And that brings us to the ultimate question. What is the fate of our universe? Will the expansion accelerate until it tears everything apart in a big rip? Will it lead to a cold, dark, big freeze, where the universe fades to black? Or could something cause the expansion to reverse, leading to a cosmic collapse in a big crunch? For a long time, the big crunch was seen as unlikely, but some recent observations hint that dark energy might not be constant, which could make a future collapse possible again. The ultimate fate of everything hinges on understanding the true nature of this expansion we are only just beginning to grasp. Science confirms the universe has no outside. Picture this. You're an ant on the surface of a vast, red balloon. To you, your world is a two-dimensional plane that seems to go on forever. You can walk in any direction, forward, backward, left, right, and you'll never find an edge. You won't stumble upon a sign that says, "The end is near," and you certainly won't fall off. Your world, for all you know, is infinite. Now, someone starts blowing up the balloon. All of a sudden, you notice something weird. Your friend, another ant who was just a short walk away, seems to be moving away from you. In fact, every ant, everywhere on the balloon, is moving away from every other ant. The space between you is literally growing. Your world is expanding. But what is it expanding into? From your limited, two-dimensional point of view, the question just doesn't make sense. Well, what if I told you that we are all that ant, and the balloon is our universe? It's a single idea, backed by a century of mind-bending science, that completely changes how you see reality. It takes one of the most basic questions we could ever ask: what's outside the universe? and reveals that the question itself is the mistake. Understanding this will rewire your perception of space, time, and your own place in the cosmos. The promise: a new reality. For as long as humans have looked at the stars, we've thought in terms of boundaries. The horizon, the walls of a valley, the edge of a forest. Our brains are wired to see containers and wonder what's outside them. So when we look into that deep, star-dusted blackness, our intuition screams. Where does it end? If the universe is getting bigger, it must be expanding into something. Some even bigger, emptier space, right? This is where our everyday intuition completely fails us. We're about to follow the breadcrumbs left by giants like Einstein and Hubble, whose work revealed our universe is anything but static. We'll see that the Big Bang wasn't an explosion in space, but an explosion of space itself. That one little word change makes all the difference. By the end of this, you'll understand why asking, "What's outside the universe?" is, to a physicist, like asking, "What's north of the North Pole?" You'll see how something can be finite yet have no edge, and how space can stretch without needing anything to stretch into. It might feel like a mental knot, but once we untie it, the universe becomes a much stranger, and far more wonderful, place. This isn't just a fun thought experiment. It's the reality our cosmological data points to. So, let's go back to our friend on the balloon and really understand its world, because it's the perfect model for our own. The ant's world, deconstructing the analogy. Let's really get to know this two-dimensional ant. This isn't just a cute story. It's a powerful tool for grasping ideas our three-dimensional brains struggle with. Our ant lives on the 2D surface of the balloon. It knows length and width, but has no concept of up or down. That third dimension is as alien to it as a fourth spatial dimension is to us. Now, imagine this ant is a scientist. It has its own physics, its own math. Its entire reality is the rubber skin of the balloon. At first, exploring its local neighborhood, the world would seem perfectly flat. Triangles have angles that add up to 180 degrees. Two friends walking in parallel lines will stay parallel forever. It's the simple Euclidean geometry we learned in school. But our ant is curious. It builds powerful telescopes and starts looking at things that are very, very far away. It notices that two beams of light starting off parallel don't stay that way over immense distances. They slowly bend toward each other. And here's the real shocker. If the ant walks in a perfectly straight line for a long, long time, it eventually arrives right back where it started, but from the opposite direction. From these clues, the ant scientist makes a revolutionary discovery. Its universe isn't an infinite flat plane, it's curved. It's a finite space, but it has no boundary. It's what we'd call a finite, unbounded, two-dimensional surface. The ant can walk forever and never fall off because the space loops back on itself. It can figure all of this out from within its 2D universe, just by measuring geometry over vast distances. Now, let's add in the expansion. The balloon is being inflated. The ant scientist sees that distant ant colonies are all moving away, and the farther away they are, the faster they're receding. The ant might think it's at the center of everything. But then it talks to other ant scientists in faraway colonies, and they all report the exact same thing. Everything is moving away from them. This is the eureka moment. There is no center. The expansion is happening everywhere at once. The very fabric of their 2D space is stretching. The distance between any 2 points is growing not because they're running from each other, but because the space between them is being created. So when the ant asks, "What is my universe expanding into?" it's trying to apply outside logic to a self-contained system. It pictures its 2D surface expanding into a 3D room, but for the ant, that third dimension doesn't exist. The expansion is an intrinsic property of its universe. The surface area is simply increasing. It's not taking over new territory. Its own territory is just getting bigger. This is the exact leap of intuition we now have to make. From balloon to cosmos, scaling up our reality. Okay, let's leave the ant to its cosmic revelations and scale up the analogy. The ant's 2D world was curved through a 3D space it couldn't perceive. Our universe is a 3D space. We have length, width, and height. So, if our universe is curved, it would be the 3D surface of a 4-dimensional sphere, or a hypersphere. This is where our brains tend to sputter. We can easily picture a 2D sheet curving into a 3D ball. But what does a 3D space curving through a fourth spatial dimension even look like? The honest answer is, we can't visualize it. Our minds evolved to throw spears, not to picture 4D geometry. But here's the secret that unlocks the whole thing. We don't need to. Just like the ant didn't need to see the third dimension to know its universe was curved, we don't need to see a fourth dimension to measure our own. Einstein's general theory of relativity describes the universe's geometry from the inside out. The math tells us how space, time, and matter create curvature without ever mentioning an outside for it to curve into. That higher dimension is just a crutch for our imaginations. If our universe is positively curved, like the balloon, it would be finite in volume but have no boundaries. If you flew a spaceship in a straight line for an incomprehensibly long time, you'd eventually arrive back at Earth from the opposite direction. You would have circumnavigated the cosmos. And the expansion? Just like the balloon, the expansion of our universe is the stretching of spacetime itself. The galaxies aren't flying through space like shrapnel. That's the single biggest misconception about the Big Bang. They are more like raisins in a loaf of bread rising in the oven. The raisins aren't moving through the dough. They're being carried apart as the dough itself expands. When we see the light from distant galaxies, redshifted, stretched to longer wavelengths, we are seeing this cosmic expansion in action. It's not the sound of a passing siren. It's the light wave itself being stretched by the expansion of space during its long journey to us. Edwin Hubble first saw this in the 1920s, providing the first solid proof that our universe is a dynamic, evolving place. So, the question, what is the universe expanding into, is built on a faulty premise. It assumes the universe is an object expanding within a larger space. But our best science says the universe is space. All of it. The expansion is just an increase in the distance between its parts. It doesn't need an outside to expand into, any more than the number line needs a place to go when you keep counting. The echo of creation. Evidence in ancient light. This all sounds like a lovely mathematical story, but where's the proof? The evidence is written across the entire sky, in the oldest light in the universe. Part A. The redshift revolution. A little over a century ago, astronomers thought the universe was just our Milky Way galaxy. Other fuzzy patches in the sky, called nebulae, were believed to be gas clouds nearby. But then, an astronomer named Vesto Slipher noticed that the light from most of these nebulae was shifted toward the red end of the spectrum, meaning they were moving away from us at incredible speeds. The missing piece was distance. That piece came from Henrietta Swan Leavitt, who discovered a way to measure vast cosmic distances using special stars called Cepheid variables. In the 1920s, Edwin Hubble used her method and the world's most powerful telescope to discover that these nebulae were actually other galaxies, island universes, millions of light years away. Suddenly, the known universe got a whole lot bigger. But Hubble didn't stop there. He measured the distances and redshifts of dozens of galaxies and found a stunning pattern. The farther away a galaxy was, the faster it was receding from us. This became known as Hubble's law. The universe wasn't static, it was expanding. This was the first observational pillar for the Big Bang. Part B. The cosmic microwave background. If the universe is expanding, then in the past, it must have been smaller, denser, and hotter. Physicists like George Gamow realized that going back far enough, the universe would have been an opaque, glowing fog of plasma, too hot for atoms to form. Light would be trapped, scattering off electrons like headlights in a thick fog. They predicted that as the universe expanded and cooled, it would eventually hit a point where atoms could form, setting all that trapped light free. This afterglow of the Big Bang, they calculated, should still be detectable today, cooled and stretched by 13.8 billion years of expansion into the microwave part of the spectrum. For decades, this was just a theory. Then, in 1964, two radio astronomers, Arno Penzias and Robert Wilson, were trying to get a new antenna working and were bothered by a persistent background hiss coming from every direction. They even cleaned out pigeon droppings, but the hiss remained. It turns out they had accidentally stumbled upon the echo of creation. They had found the cosmic microwave background, CMB. This was a Nobel Prize-winning confirmation of the Big Bang. We are literally bathed in the leftover heat from the birth of the universe. Satellites like WMAP and Planck later mapped this light in incredible detail, finding tiny temperature fluctuations differences of 1 part in 100,000. These tiny ripples were the gravitational seeds that grew into every galaxy, star, and planet we see today. But most importantly, they hold the key to the universe's geometry. The shape of everything, flat, spherical, or hyperbolic. Those tiny temperature spots in the ancient CMB light have a characteristic size that physicists could calculate. They give us a cosmic ruler. By measuring the apparent size of those spots in the sky today, we can figure out the geometry of the space that light has traveled through for 13.8 billion years. Think of it like looking at a coin at the bottom of a pool. If the water's surface is flat, the coin looks normal. But a curved surface can act like a lens, making the coin look bigger or smaller. Einstein's theory allows for 3 basic shapes for the universe. 1. A closed, spherical universe, like the balloon. Here, gravity is strong enough to eventually stop the expansion and pull everything back into a big crunch. Parallel lines eventually cross, and the CMB spots would look larger than expected. 2. An open, hyperbolic universe, shaped like a saddle or a Pringles chip. Here, there isn't enough gravity to stop the expansion, and it goes on forever. Parallel lines curve away from each other, and the CMB spots would look smaller than expected. 3. A flat, Euclidean universe. The just right scenario. Here, the expansion coasts forever, slowing down but never stopping. Parallel lines stay parallel, and the CMB spots would look exactly the size theory predicts. So, what do we see? After years of mapping by the Planck satellite, the results were astonishingly clear. The spots are the size they should be. The data shows that, on the largest scales, our universe is almost perfectly flat. This is a profound result, suggesting the universe is likely infinite in extent. Now, science is never totally settled. Some analyses of the Planck data hint at a slight positive curvature, which would mean the universe is closed and finite, just so mind-bogglingly huge that it looks flat to us, the same way the Earth looks flat from your backyard. This is part of an exciting, ongoing debate in cosmology, and future data from projects like the Euclid telescope will help us sharpen these measurements. But whether it's a truly infinite flat sheet or a gargantuan sphere, the conclusion for us is the same: there is no edge. The ultimate misconception. What is it expanding into? We've arrived at the final hurdle, the question our brains just can't let go of. If it's getting bigger, how can there be no outside? This is where we have to finally reject the idea of the Big Bang as a bomb going off in an empty room. That mental image is the source of all the confusion. It implies a center, an edge, and a pre-existing void. All of that is wrong. The Big Bang happened everywhere. Let that sink in. It wasn't an event in space. It was the beginning of space and time. At the very start, every point in our vast universe today was compressed into the same unimaginably hot, dense state. The expansion began everywhere at once. Think back to the balloon. Is there a center to the expansion on its surface? No. Every point moves away from every other point. It's the same for us. We aren't watching the expansion from a special seat, we are in it. So, what is it expanding into? Itself. Spacetime isn't a static stage, it's a dynamic thing that can stretch. The expansion is simply the distance between 2 points in space increasing over time. As Stephen Hawking famously put it, asking what the universe is expanding into is like asking what is north of the North Pole. The question misunderstands the concept. The universe, by definition, is all of space. There's no outside location for it to expand into, because the idea of location only makes sense within our universe. It is the whole show. The stage itself is getting bigger. There's no backstage. The edge of seeing versus the edge of being. There's one last common point of confusion. The edge of the observable universe. Isn't that an edge? No. It's not a physical wall. It's a horizon of information, created by the finite speed of light and the finite age of the universe. The universe is about 13.8 billion years old. That means we can only see objects whose light has had 13.8 billion years to reach us. Anything farther away is, for now, beyond our view. The sphere around us containing everything we can see is the observable universe. Its radius today is roughly 46.5 billion light-years, because space itself expanded while the light was traveling. This is an edge of seeing, not an edge of being. It's like being on a ship in the middle of the ocean. You see a horizon in every direction, but you know the ocean doesn't just stop there. An alien in a galaxy at the edge of our observable universe has its own observable universe, which includes parts of the cosmos that are currently invisible to us. The universe almost certainly continues on far beyond what we can see, filled with more galaxies, looking much the same as it does here. Our observable bubble is just our current window onto that grander, edgeless reality. If your brain feels like it's expanding right along with the universe and you want to explore more of these incredible realities, think about subscribing. We tackle the biggest questions in physics and cosmology every week. Hit that subscribe button and turn on notifications so you don't miss our next trip into the cosmos. We'd love to have you in our community of cosmic explorers. Beyond the boundary. Whispers of other universes. Okay, so our universe has no outside. But that hasn't stopped physicists from asking an even wilder question. Could our universe be just one piece of a much larger reality? This is where we step from established science into the fascinating, speculative frontier of theoretical physics. One idea is Stephen Hawking and James Hartle's no-boundary proposal. It uses quantum mechanics to describe the birth of the universe. In this view, if you rewind time all the way back, the distinction between time and space dissolves. Time behaves like another dimension of space. The universe doesn't have a sharp starting point in time. It has a smooth, rounded origin, like the South Pole on Earth. At the South Pole, south stops having meaning. At the beginning of the universe, before stops having meaning. As Hawking said, the boundary condition of the universe is that it has no boundary. Other ideas, like the multiverse, suggest our Big Bang wasn't a one-off event. Some theories of cosmic inflation predict that new, bubble, universes are constantly branching off, each with its own Big Bang and maybe even its own laws of physics. Then there's Brane cosmology, from string theory, which proposes our 3D universe is a brane, floating in a higher dimensional space called the bulk. Other universes could be floating parallel to our own, maybe just a tiny distance away in that extra dimension, but forever out of reach. It's vital to remember these are speculative ideas. They exist at the very edge of our mathematics and currently have no direct experimental evidence to back them up. But they show that even after figuring out our universe has no outside, human curiosity just keeps pushing, redefining what universe and existence could even mean. The unbounded journey. We're back where we started, as an ant on a balloon. That simple picture took us on a wild ride. We've seen that our universe is an expanding fabric of spacetime, and the Big Bang was an explosion of space, happening everywhere at once. We've looked at ancient light and found that our universe is incredibly flat, suggesting a reality that's either infinite or just too colossal for us to see the curve. The takeaway is as profound as it is inescapable. Our universe has no outside. The question falls apart when you realize the universe is, by definition, everything. All of space, all of time, all matter and energy, all in one self-contained system. There is no edge to fall off of and no wall to run into. This changes our place in the cosmos. We're not in a tiny room looking out a window. We are voyagers on a cosmic ocean that is both finite in its properties and endless in its possibilities. We are that ant, forever exploring a reality that has no edge. The sky above you isn't a ceiling, it's just deeper water. And every distant galaxy we find isn't a step closer to an end, but just a deeper dive into the magnificent, boundless, and mind-bending universe that is our home. The biggest lie you were taught about the universe. You know the image. It's maybe the most common explanation for our expanding universe. A teacher grabs a balloon, draws a few dots on it, and starts to inflate it. As the balloon grows, all the dots are galaxies move away from each other. It's simple. It's intuitive. And for millions of us, it's the main picture we have in our heads when we think about the cosmos getting bigger. But what if I told you that this one analogy, taught in schools and science shows for decades, has secretly created a massive misunderstanding about the very nature of reality? What if the simple tool designed to make cosmology easy has instead built a fundamental lie into how we think? A lie that sends us down a completely wrong path when we ask the biggest questions of all. Where did everything come from? What is it expanding into? And where's the edge? Today, we're popping that balloon. We're going to look at the comfortable, easy picture it paints, and then we're going to tear it apart. Because by understanding why the balloon analogy is so wrong, we can finally start to get what's really happening out there. This isn't just about fixing a tiny scientific detail. It's about rewiring our core understanding of space, time, and existence itself. So stick around, because the universe on the other side of this lie is far stranger, and way more magnificent, than a party balloon could ever show you. The seductive simplicity. What the balloon gets right. Alright, before we start tearing it down, let's give the balloon some credit. It's popular for a reason. In a couple of really important ways, it's actually a brilliant teaching tool. It's a great way to introduce some of the weirdest ideas in science, ideas that completely shattered our view of the cosmos a century ago. The first big thing the balloon gets right comes from Edwin Hubble's work back in 1929. Using the best telescopes of his day, Hubble measured the light from faraway galaxies and found something mind-blowing. Pretty much every galaxy he looked at seemed to be moving away from us. And it was more specific than that. He found a clear pattern, what we now call Hubble's law. The farther away a galaxy is, the faster it seems to be running away. This is where the balloon analogy just shines. Picture yourself as a tiny ant on one of those dots. As the balloon inflates, you watch the other dots. The one right next to you moves away slowly. But a dot on the far side of the balloon seems to be racing away. From your perspective, it really looks like you're the center of everything. And this is the second bit of genius: if you hopped over to any other dot, you'd see the exact same thing. From every single dot's point of view, all the other dots are moving away, and the farthest ones are moving fastest. There's no special, central dot. This perfectly illustrates a core idea in cosmology called the cosmological principle. It's a fancy way of saying that on the biggest scales, the universe is pretty much the same everywhere and in every direction. There are no special spots. No center. Our galaxy isn't the heart of the universe, and neither is any other. The third thing the balloon helps us see is the asterisk nature of the expansion itself. The dots, the galaxies, aren't flying through space like pieces of cosmic shrapnel. Instead, the space between the galaxies is what's expanding. The galaxies are just being carried along for the ride. This is a crucial concept called metric expansion. It means the very fabric of the universe, the thing that defines distance, is stretching. The universe isn't getting bigger by moving into some empty void. The universe itself is stretching. A better analogy for this part is a loaf of raisin bread dough rising. The dough is space, the raisins are galaxies. As the dough expands, all the raisins move apart, but they aren't moving through the dough. They're being carried by it. And finally, the balloon hints at something even stranger. The idea of a universe that's finite but has no edge. The surface of a balloon has a limited area, but an ant could walk on it forever and never fall off. It might even end up right back where it started. This is one possible shape for our universe. It could contain a finite amount of space, but have no boundary to speak of. So, yeah, the balloon shows us that distant galaxies recede faster, there's no center, space itself stretches, and the universe could be finite but unbounded. For a simple toy, that's pretty good. But that first step leads us right off a cliff of misunderstanding. The first crack, the expanding into what? Problem. Every time you blow up a balloon, you do it inside a room. The balloon's 2D surface expands within our 3D space. It pushes against the air, taking up more volume. Our brains see this, and our intuition, trained by a lifetime of living in a 3D world, immediately jumps to a conclusion. One thing is expanding into something else. And so we ask the question that feels perfectly logical. What is the universe expanding into? Almost everyone who thinks about the cosmos asks this. And the balloon analogy is almost single-handedly to blame, because it locks our brains into a framework where that question makes sense. The balloon has an inside and an outside. But for the universe, that's the biggest lie. The expansion of the universe is not an expansion into anything. There is no outside. There's no bigger, emptier void that our cosmos is slowly filling up. The question itself is broken. It's like asking, what's north of the North Pole? The expansion is an asterisk intrinsic change of spacetime itself. It's not an event happening in space, it's space itself that's changing. Remember the stretching fabric? That's the whole story. The distances between things that aren't held together by gravity are increasing because the scale of space itself is increasing. Our modern theory of gravity, general relativity, describes space-time as a dynamic, flexible thing. The Friedmann equations, born from Einstein's theory, show that the universe can't just sit still, it has to be either expanding or contracting. And our observations confirm it's expanding. But this expansion is a change in the geometry of the entire system. It doesn't need a higher dimension to expand into. The universe, by definition, is everything. So there can't be an outside. It is, in a very real sense, expanding into itself. Letting go of that deep-seated need for an outside is the first, and most important, step to undoing the lie of the balloon. The second crack, the myth of the center. The balloon analogy has another, sneakier flaw that feeds a different misconception. The idea of a center of the universe. Sure, the asterisk surface of the balloon does a great job showing there's no center on that 2D plane. But we can't help but see the whole 3D balloon. And where does the air come from? From a single point, your mouth. The balloon inflates outwards from a central point in 3D space. Our brains see that and subconsciously file it away. Expansion comes from a center. This reinforces the most common myth about the Big Bang, that it was an explosion that happened at a single point in space. We imagine a tiny, dense dot that went bang, flinging galaxies out into a pre-existing emptiness. If that were true, there would be a center, the spot where the bomb went off. But that picture is completely wrong. The Big Bang didn't happen at a point in space. It happened everywhere in space at once. This is another one of those mind-bending ideas, but it follows directly from what we already know. If the universe is basically the same everywhere, then the Big Bang must have happened everywhere. In the first moments of the universe, all of space was incredibly hot and dense. It wasn't a tiny speck sitting in an endless void. The point that cosmologists talk about is a point in time, not space. It was the moment the expansion kicked off. So at time zero, the entire universe, which might have already been infinite, was in this super-dense state, and it began expanding everywhere simultaneously. The Big Bang was an explosion of space, not an explosion in space. This means there is no center of the universe. Or, put another way, everywhere is the center. Right now, you can claim to be at the center of your observable universe. An alien in a galaxy a billion light-years away can make the exact same claim. Both of you would look out and see everything else receding from you. Neither of you would be wrong. The third crack, the stretchy fabric and the unstretched galaxy. The third big flaw with the balloon is the one that feels most like a contradiction. The balloon is made of rubber. When it inflates, the rubber stretches. If you draw a little circle on it, the circle itself gets bigger. The ink lines spread out. This leads to a really good question. If the fabric of space is stretching, why aren't we stretching with it? Why isn't the Earth getting bigger? Why isn't our solar system expanding? Why don't galaxies themselves get ripped apart? The balloon analogy says they should. But they don't. And the reason is that on a local scale, the expansion of the universe is incredibly, fantastically weak. The expansion is happening everywhere, right now, inside the atoms of your body. But the electromagnetic force holding your atoms together is many, many orders of magnitude stronger. For protons in a nucleus, the force of gravity is about 10 to the power of 36 times weaker than the electromagnetic force, and the force of cosmic expansion over that tiny distance is even more negligible. There is zero danger of you, your chair, or this planet being stretched apart by the cosmos. What about bigger things, like our solar system? Again, no. The sun's gravity completely overpowers the gentle stretch of spacetime. Earth's orbit is not getting one bit larger because of cosmic expansion. Even on the scale of our entire Milky Way galaxy, the hundreds of billions of stars are all held together in a tight gravitational dance. That collective gravity is far too strong for the expansion to have any effect. In fact, our nearest galactic neighbor, Andromeda, is actually moving towards us. We're on a collision course because on our local scale, gravity is still king. It's only when you get to the truly vast, empty distances between clusters of galaxies that the slow, steady expansion of space finally wins out. Over millions of light years, there isn't enough matter to hold things together, so the space between them stretches, and the great galactic clusters drift away from each other on an ever-expanding cosmic ocean. The balloon, with its uniform stretching, just gets this part wrong. Alright, we've popped the balloon. We've seen how this simple analogy, while useful, leads us to ask the wrong questions and build a flawed picture of reality. We've thrown out the lies of an outside, a center, and a stretchy everything. This whole process questioning old ideas and replacing them with better ones is what science is all about. And if you enjoy thinking about these huge cosmic questions, take a second to subscribe and hit that notification bell. We're always trying to get to the bottom of what we know, and we'd love for you to join us. So now that the balloon is broken, how do we build a better picture in our heads? Building a better picture. grids, redshift, and the scale factor. So how do we get a better mental model? There's no single perfect analogy, because our daily lives don't really have anything in common with general relativity. But we can combine a few ideas to get closer. First, let's go back to the raisin bread dough. This analogy is better than the balloon because it correctly shows that the gravitationally bound raisins, galaxies, don't expand, while the dough between them, space, does. It helps fix that stretching everything problem. Second, think of an infinite sheet of graph paper. The expansion of the universe is like the grid itself stretching out. The lines get farther apart. The sheet isn't expanding into anything, because it's already infinite. The distances within the sheet are just scaling up. This idea of a scale factor is what cosmologists actually use. They use a number, a, t, to describe how stretched the universe is at any given time. Today, the scale factor is 1. In the past, it was less than 1. In the future, it will be greater than 1. The equations tell us how this number changes over time based on what's in the universe, like matter and dark energy. The whole story of the cosmos is really the story of this changing scale factor. But how do we know any of this is happening? We can't see the grid lines of space. The proof is in the light. This brings us to cosmological redshift. You already know the Doppler effect. An ambulance siren sounds high-pitched as it comes toward you and low-pitched as it moves away. That's because the sound waves get compressed, then stretched. The same thing happens to light. If a star is moving away from us, its light waves get stretched, shifting them to the red end of the spectrum. For a while, that's what we thought we were seeing. But it's something more profound. When light from a distant galaxy travels for billions of years to reach us, the space it's traveling through is expanding. So the light wave itself gets stretched out along with space. This isn't because the galaxy is flying through space, but because the space between us and the galaxy has grown. The more the light is redshifted, the more space has expanded since that light began its journey. So our new mental picture is a universe where galaxies are like unstretching raisins in an expanding dough of spacetime. And we can see the dough expanding by measuring how much the light traveling through it has been stretched. The edge of reality, the observable universe. Okay, so if the universe has no edge, does that mean it's infinite? And if it has no center, why does it seem like we're surrounded by a boundary? This brings us to the final piece of the puzzle. The difference between the universe and the observable universe. The universe has a finite age, about 13.8 billion years. Since nothing can travel faster than light, that sets a hard limit on how far we can see. We can only see things if their light has had enough time to reach us. This creates a sphere around us. The edge of that sphere is our observable universe. It's our cosmic horizon. Anything beyond that horizon, light from it just hasn't reached us yet. Now, you might think that sphere would have a radius of 13.8 billion light years, but because space itself has been expanding while that light was traveling, the object that emitted it is now much farther away. Current estimates put the radius of our observable universe at around 46.5 billion light years, though that number can vary slightly depending on the exact models used. But here's the key. It's a horizon, not a physical edge. Think of being on a boat in the middle of the ocean. You can see to the horizon in every direction, but you know the ocean doesn't just stop there. And if you sail for a day, you're still in the center of your own personal horizon. That's exactly what the observable universe is like. Every observer, everywhere in the cosmos, is at the center of their own cosmic horizon. And all our evidence suggests the universe keeps going well beyond what we can see, with more galaxies, more clusters, and more voids, stretching on and on. So could the whole universe be infinite? It's very possible. Our best measurements show that space is almost perfectly flat on large scales. While a flat universe could have a weird, finite topology, the simplest explanation for a flat geometry is an infinite one. We can't prove it, but we know for sure that the universe is vastly, colossally bigger than the part we can see. The modern mystery, the Hubble tension. So, we've dismantled the bad analogy and built a better, truer picture. You might think we've got it all figured out. But right now, cosmology has a huge, nagging mystery, and it's all about the very rate of expansion we've been talking about. It's a crisis known as the Hubble tension. Simply put, we have two extremely precise ways of measuring how fast the universe is expanding, and they are giving us two different answers. The first method looks at the early universe. We study the cosmic microwave background, the leftover heat from the Big Bang. By studying the patterns in this ancient light from when the universe was just 380,000 years old, our standard model of cosmology predicts an expansion rate today of about 67 kilometers per second per megaparsec. The second method looks at the late universe, the one we see around us today. Astronomers use things called standard candles, like certain types of stars and supernova explosions, where we know their true brightness. By seeing how dim they look, we can calculate their distance, and by measuring their redshift, we can see how fast they're moving away. This direct, local measurement gives us a faster expansion rate, about 73 kilometers per second per megaparsec. For years, scientists hoped the problem was just a measurement error. But as our telescopes get better and better, the disagreement has only gotten stronger. It's a real crisis. What could be causing it? Are our local measurements wrong? Is our understanding of the early universe flawed? Or, the most exciting possibility, is our standard model of cosmology itself missing something? Maybe there's a new type of particle or force we don't know about. Maybe dark energy isn't so constant after all. The Hubble tension is a perfect example of science in action. We built a model that worked beautifully for decades. But now, better data is showing cracks in the foundation. This is how progress happens. This is how we figure out what we don't know. The story of cosmic expansion is far from over. We started with a simple party balloon. It's a comfortable image, but it's a lie. The universe isn't expanding into an outside. The Big Bang didn't happen at a central point. And you are not stretching apart with the fabric of space. The reality is so much more incredible. We live in a cosmos where space itself is alive, stretching the voids between great islands of galaxies. A universe where the beginning happened everywhere at once. A universe that might be infinite, where the only edge is the limit of our own view. Letting go of the balloon is about more than just scientific accuracy. It's about accepting that the cosmos doesn't have to make sense in the way our everyday world does. It pushes us to wrestle with ideas that are truly strange and beautiful. The universe isn't a simple thing happening in a familiar room. It is the room, the thing, and the rules all at once, a tapestry of spacetime being woven moment by moment, everywhere. The lie of the balloon gave us an easy answer. The truth of the cosmos gives us something infinitely better, a genuine sense of wonder. So, what other cosmic myths should we tackle next? Let us know in the comments. Your curiosity is what drives this channel. If you want to keep questioning the universe with us, make sure you're subscribed and maybe check out this other video on another mind-bending topic. The universe's hidden shape controls your fate. We think we know the basics. We live on a planet, orbiting a star, in a galaxy that's adrift in a cosmos so vast it's almost impossible to wrap your head around. And for most of us, that's where the picture stops. The universe is just there. A dark, endless room. A flat, infinite stage for everything else to happen on. It's the very definition of emptiness. But what if that's the biggest mistake we've ever made? What if the stage itself has a secret shape? Clues are now emerging from the embers of the Big Bang that suggest our universe has a hidden architecture. It's a shape we can't see, but one that's quietly deciding the ultimate fate of everything and everyone. This isn't just about geometry anymore, it's about destiny. And the answer is turning out to be far stranger, and way more important, than anyone ever dreamed. The flat reality we thought we knew. For decades, our map of everything has been the standard model of cosmology. It was built on a simple, powerful idea. On the biggest scales, the universe is flat. Not flat like a pancake, but geometrically flat. In a flat universe, the rules you learned in high school geometry apply everywhere. If you shot two parallel lines of light across the cosmos, they'd stay parallel forever. They'd never meet, and they'd never drift apart. The three angles of a giant triangle with corners billions of light years apart would add up to a perfect 180 degrees. This idea wasn't just a guess. It came straight from our best theory for the universe's birth, called cosmic inflation. Inflation says that in the very first split second after the Big Bang, the universe blew up at a ridiculous speed, swelling from smaller than an atom to astronomically huge, almost instantly. Think about inflating a tiny, crumpled balloon to the size of the entire Earth. If you were an ant standing on its surface, the ground would look perfectly flat. Inflation, scientists argued, did the exact same thing to the universe, smoothing out any original curves until it was basically flat. And we saw the proof, again and again. Probes like NASA's WMAP and the European Space Agency's Planck satellite measured the oldest light in the universe, the cosmic microwave background, a faint glow from the dawn of time. The evidence seemed crystal clear. Our universe was flat, with a margin of error so tiny it was like measuring the width of North America down to a single millimeter. A flat universe came with a specific fate. It was perfectly balanced, with just enough stuff in it to slow its expansion over time, but not quite enough to ever stop it. The consensus was that the universe would expand forever. The galaxies we see are all drifting apart, like dots on an endlessly inflating balloon. And that's a key point. The galaxies aren't flying through space. The space between them is stretching, carrying them along for the ride. It was a neat, if lonely, picture of our home of flat, infinite space, doomed to a quiet, cold, eternal future. For a while, it seemed like we had the big picture all figured out. But the whole point of science is to poke at the edges of what we know, and in the late 1990s, astronomers found a loose thread that would unravel everything. The first crack in the mirror, an accelerating mystery. The expectation was simple. Gravity pulls things together, so it should be acting like a giant brake on the universe's expansion. The combined pull of all the stars, galaxies, and invisible dark matter should be slowing the whole show down. So, a few teams of astronomers set out to measure exactly how much it was slowing, using distant exploding stars called Type Ia supernovae as cosmic mile markers. What they found was the exact opposite. The expansion wasn't slowing down at all. It was speeding up. This discovery rocked the scientific world and earned its leaders a Nobel Prize. It meant some other, mysterious force was out there, a repulsive energy that was pushing everything apart and winning the fight against gravity. They gave it a name, dark energy. According to our best data from the Planck satellite, this weird stuff makes up over 68% of the universe. The normal matter that makes up you, me, the stars, and planets? That's less than 5%. We live in a cosmos dominated by things we can't see and don't understand. This didn't just add a new ingredient to the cosmic recipe, it created a huge problem. It forced us to ask, if our best model of the universe couldn't even predict what it's doing right now, how sure can we be about its most basic property, its shape? This doubt has grown into what some are now calling a cosmological crisis. There's another huge puzzle, the Hubble tension, which is just a fancy way of saying our measurements of the expansion rate don't agree. When we measure the expansion rate of the universe nearby, we get one number. But when we use our model of the early universe based on that baby picture from the Planck satellite to predict what the rate should be today, we get a different, slower number. They should match. They don't. It's like having a growth chart for the universe where the height predicted from its baby photos doesn't match its actual adult height. This stubborn disagreement is a giant red flag that our standard model might be broken, or at the very least, missing a piece. And if the model's broken, then everything it's built on, including the idea of a flat universe, has to be questioned. The acceleration was the first sign something was deeply wrong. It sent detectives back to the scene of the crime, the very beginning of time, to look for the true shape of space itself. The cosmic detective story, hunting for the shape. So, how do you measure the shape of the entire universe when you're stuck inside it? You can't step outside and take a look, so you have to be clever. You have to look for the fingerprints that geometry leaves on the light that travels across the cosmos. And our best tool for that is the cosmic microwave background, or CMB. The CMB is literally the oldest light in the universe, a snapshot from just 380,000 years after the Big Bang. Before then, the universe was a hot, dense fog of particles and radiation. Light couldn't go anywhere, it was just constantly bouncing off electrons. But as the universe expanded and cooled, electrons and protons finally paired up to form the first atoms. All at once, the fog cleared. The light that was there in that instant was finally set free, and it's been traveling across space for the last 13.8 billion years. Today, that ancient light washes over us from every direction as faint microwaves. The Planck satellite gave us the most detailed map of this light ever made. It's not a perfectly smooth glow. It's covered in tiny hot and cold spots, which were the seeds of all the galaxies and stars we see today. And hidden in those spots is the key to the universe's geometry. Cosmologists use these spots to basically draw the biggest triangle in the universe. They know the actual, physical size of these hot and cold spots in the early universe, and they can measure how big they appear to us in the sky today. With a little trigonometry, they can check if the geometry adds up. If the universe is flat, the angles of this cosmic triangle work out to 180 degrees. If the universe is curved, the light gets bent on its journey, and the angles will look different. But there's another clue hiding in the CMB: gravitational lensing. Einstein taught us that massive objects warp space. So as that ancient CMB light travels for billions of years, its path gets slightly bent and warped by the gravity of all the galaxies and dark matter it passes. This lensing effect subtly blurs the CMB's hot and cold spots in a predictable way. The amount of blurring tells us how much stuff is in the universe, which is directly tied to its overall shape. And it was in this subtle blur that a team of scientists in 2019 found something that threatened to break cosmology completely: the three faces of fate. Before we get to that, you need to know the options. When cosmologists talk about the shape of the universe, they're really talking about its curvature. And there are only three basic possibilities, each with its own geometry and its own unique destiny. Let's use some snack food analogies. First, you have a flat Triscuit cracker. This is a flat universe with zero curvature. This is the one where high school geometry works, and parallel lines stay parallel forever. This universe has what's called a critical density. It's perfectly balanced. Pushed by dark energy, its destiny is a big freeze. Galaxies will fly apart until they disappear over the horizon. The universe will get colder, darker, and emptier until all activity just stops. An end of quiet, eternal loneliness. Next, picture a Pringle potato chip. This saddle shape is an open universe with negative curvature. Here, geometry gets weird. Parallel lines eventually drift apart. The angles of a triangle add up to less than 180 degrees. An open universe doesn't have enough stuff in it for gravity to stop the expansion. Its fate is even more dramatic than the Big Freeze. A Big Rip. The runaway expansion, driven by dark energy, would eventually become so violent it would first tear galaxies apart, then solar systems, then planets. In the final moments, it would overcome the forces holding atoms together, ripping the very fabric of matter into a soup of stray particles. Finally, imagine a cheese ball. This represents a closed universe with positive curvature. Like the surface of a sphere, it's finite, but it has no edge. If you flew in a straight line long enough, you'd loop all the way around and end up right back where you started. In a closed universe, parallel lines eventually meet, and a triangle's angles add up to more than 180 degrees. This is a universe where there's more than enough density for gravity to win the cosmic tug-of-war. For a long time, the fate of a closed universe was thought to be a big crunch. The expansion would slow, stop, and then reverse. Galaxies would come rushing back together, heating up until everything collapsed into a final, fiery singularity, a perfect mirror image of the Big Bang. For years, all the evidence pointed to option 1, the flat Trisket. But it only takes one stubborn, unexplained fact to throw everything into doubt. And that fact was hiding in the Planck satellite's data. The revelation, a crisis in the cosmos. In November 2019, the world of cosmology got a jolt. A paper published in the journal Nature Astronomy took a closer look at the final data from the Planck mission. The team, led by Eleonora Di Valentino, Alessandro Melchiori, and Joseph Silk, focused on one thing: that gravitational lensing effect in the CMB. Remember, the gravity of everything in the universe should blur the CMB light by a certain amount. But the Planck data had always shown a weird anomaly. The lensing effect was way stronger than it should be in a flat universe. The ancient light was being blurred too much, as if it had passed through more matter and therefore more gravity on its 13.8 billion-year trip to get to us. The team behind the 2019 paper offered a bold explanation. Maybe the lensing is stronger because there is more matter. And a closed, spherical universe can hold more matter. When they isolated the lensing data and ran the numbers, their conclusion was stunning. The data, they claimed, pointed to a closed universe with a statistical significance of 3.4 standard deviations. In plain English, they were saying there was a greater than 99% probability that the universe is actually a sphere. This wasn't some minor adjustment. This was a direct assault on the foundations of modern cosmology. The authors themselves said this discrepancy pointed to a cosmological crisis, and called for a drastic rethinking of the whole standard model. If the universe was really closed, it meant our ideas about inflation were wrong. It meant the universe is finite, not infinite. And it would totally change its ultimate fate, dragging the fiery, big crunch scenario back from the dead. For a moment, it felt like the floor had just dropped out from under cosmology. Decades of work were being challenged by a single piece of evidence from our best ever telescope. The comfortable, flat reality we thought we knew was suddenly in question, possibly replaced by a finite, spherical cosmos destined to collapse. The pushback, in defense of flatness. Now, a claim as wild as, the universe is a sphere, needs some seriously solid proof, and the rest of the scientific community was quick to jump in and check the work. The crisis was real, but what it meant was far from settled. While nobody denied the weirdness in the lensing data, most experts weren't ready to toss out the flat universe just yet. The main counter-argument was simple. You can't just cherry-pick one piece of data that you like and ignore the rest. The whole point of science is to build a picture that fits all the evidence. And while the lensing data, by itself, pointed to a closed universe, it clashed with almost everything else we know. For starters, other ways of analyzing the exact same Planck data still screamed flat. And when you combined the Planck data with other huge cosmological surveys like the BOSS project, which maps the location of millions of galaxies, the case for a closed universe just melted away. In fact, the final, official results from the Planck mission in 2018 concluded that the universe's curvature is zero, with an error margin so small it's basically perfect. The combined data still overwhelmingly points to a flat universe. So what could explain the weird lensing? The most likely answer, many scientists argued, was just a statistical fluke. In any huge, messy dataset, you're going to get random bumps and outliers. The 3.4 sigma result was interesting, but it wasn't the 5 sigma gold standard physicists need to claim a revolutionary discovery. It might just be a weird blip that'll disappear with more data. Or, it could be some subtle error in the telescope or the analysis that we haven't found yet. This whole debate shows you exactly how science works. It's a tug of war between tantalizing new clues and the mountain of established evidence. Today, the consensus is still that the universe is flat. But that 2019 paper was a huge wake-up call. It exposed a crack in our standard model. And even if it doesn't mean the universe is closed, it's a giant flashing sign that there's new physics out there waiting to be found. The twist? Beyond geometry, a fading force? For years, the cosmic endgame was tied directly to geometry. Closed universe meant a crunch, flat or open meant a freeze. But that whole idea depended on one huge assumption. That dark energy, the force speeding everything up, is constant. The theory was that dark energy is just a property of space itself, a cosmological constant, so its density stays the same as the universe expands. That means its repulsive push just gets more and more dominant over time, guaranteeing the expansion goes on forever. But what if dark energy isn't constant? What if it's a dynamic field that can change, or fade, over time? This idea, once on the fringe, is getting a serious new look, thanks to incredible new observations. In 2024, the Dark Energy Spectroscopic Instrument, (DESI) collaboration released the most precise map of the universe's expansion history ever. And buried in their data was a tantalizing, though not yet definitive, hint that dark energy might be getting weaker. And that's not the only clue. Other recent studies looking at those type Ia supernovae, the very things that helped us discover dark energy, have also found hints that the cosmic acceleration might be slowing down. One team, looking at data in late 2025, argued that if their findings hold up, it would demand a major paradigm shift in cosmology. The popular idea that the universe will expand forever would be completely overturned. This idea of a changing dark energy is sometimes called quintessence. Unlike a constant, its strength can evolve. And if these early hints are right, the implications for the universe's fate are absolutely staggering. It means destiny isn't set in stone. It's an unfolding drama, a battle between the fading push of dark energy and the relentless pull of gravity. And it opens the door to a truly shocking possibility: the return of the crunch. If dark energy is fading, then the future of the universe is anyone's guess. Think of a rubber band being stretched. Dark energy is the force pulling it apart, while gravity is the tension in the band trying to snap it back. For the last few billion years, the outward pull has been winning. But if that force starts to weaken, the elastic pull of gravity, which never goes away, could eventually take over again. This has brought the Big Crunch roaring back to life, but in a totally new way. A collapse might not need a closed, spherical universe after all. Even a geometrically flat universe could be doomed to recollapse if dark energy just fizzles out, or, even more dramatically, if it flips from a push to a pull. Several recent studies have looked at this exact possibility. In early 2026, one physicist at Cornell, crunching the new data from dark energy surveys, calculated a possible lifespan for our universe. In his model, the universe is about 13.8 billion years old now and will keep expanding for another 11 billion years. Then, after it reaches its maximum size, it will start to shrink, collapsing back to a single point in a big crunch, about 20 billion years from now. That would mean the universe is already past the halfway point of its life. Another team came to a similar conclusion, stating that if the universe is already starting to decelerate, then a big crunch is now a possibility. This completely rewrites the end of the story. The quiet, cold big freeze is no longer a sure thing. Instead, our distant descendants might see the galaxies in the night sky stop running away and start coming back, their light shifting from red to blue as they hurtle toward a final, spectacular collapse. What if it's not a sphere, but a donut? And just to make things even weirder, there's another layer to this whole shape business: topology. Geometry tells you about local curves: flat, open, or closed. Topology tells you how space is connected to itself on a global scale. It's totally possible for the universe to be geometrically flat, but finite. Think of a classic video game like Asteroids. You fly your ship off the right side of the screen, and you instantly pop back in on the left. You go off the top, you appear at the bottom. The screen itself is a flat, 2D surface, but it's finite and it wraps around. Now imagine that in 3 dimensions. That's the idea of a 3 torus, a universe shaped like a hyperdimensional donut. It would be perfectly flat everywhere. Triangles would still have 180 degrees, but it would be limited in size. If you traveled in a straight line, you would eventually loop right back to where you started, without ever hitting a wall. In a universe like that, you could, in theory, look out with a powerful enough telescope and see the back of your own head from light that has traveled all the way around the cosmos. Scientists are actually looking for evidence of this. They scan the cosmic microwave background for repeating patterns, or look for multiple images of the same galaxy in different parts of the sky. So far, they haven't found anything definitive. If this wrapping around exists, the scale is probably bigger than the part of the universe we can see, making it impossible to detect. But it's a wild possibility. It means that even if we prove the universe is flat, we still don't know if we live on an infinite sheet or in a cosmic hall of mirrors. This whole journey from a simple, flat cosmos to one with strange curves, fading forces, and donut-shaped realities is what makes cosmology so fascinating. We're cosmic detectives, using faint, ancient light to piece together the story of everything. Whether our universe ends in a freeze, a rip, or a crunch depends on these fundamental secrets we're just starting to uncover. So what do you think? Does a finite, spherical universe seem right? Or is the idea of a flat but loopy donut universe more compelling? Let me know your thoughts down in the comments. Our place in the grand design. We started with a simple picture, a flat, endless room. But as we've pushed to the edge of what we know, that picture has shattered into a kaleidoscope of incredible possibilities. The universe might be a sphere, a saddle, or a donut. The force driving it apart might be constant, or it could be fading away, steering us toward a future no one expected. The shape of the universe isn't just an abstract puzzle. It's the blueprint for reality. The curvature of spacetime on the largest scale determines how galaxies move, how light travels, and how the cosmic story finally ends. Our fate is literally tied to this hidden geometry. And maybe the most profound thing to come out of all this science is realizing how special our moment in time really is. As one cosmologist pointed out, we live in a golden age of information. Billions of years from now, as dark energy pushes all other galaxies beyond our view, the universe will look empty. Its true history and nature will be erased. Future astronomers would have no clue there was a Big Bang, or that a vast web of galaxies ever existed. We are, just maybe, living in the only era where the universe's grand design is still readable. We are the lucky ones who can look up and piece together the full story. In a way, we are the universe's consciousness, its brief chance to look back and understand itself. And in that reflection, we don't find a simple, static void. We find a dynamic, evolving, and deeply mysterious architecture whose final purpose remains one of the greatest secrets of all. Science just confirmed the universe is expanding into nothing. For nearly a century, we've known the universe is getting bigger. It's a fact as core to cosmology as gravity is to why we're stuck to this planet. Every distant galaxy is rushing away from every other, carried along in a cosmic current that stretches the very fabric of reality. We see them fleeing, their light stained red from its journey across billions of light years, a telltale sign of their immense and growing distance. This paints a picture of a dynamic, evolving cosmos, a huge departure from the static, clockwork universe our ancestors imagined. But here's the part that truly breaks your brain, the question that's puzzled everyone from physicists to philosophers, and probably you, too. Cosmologists agree there is no outside for the universe to expand into. No surrounding emptiness. No pre-existing void waiting to be filled. Just nothing. So, how can something get bigger if there's nothing for it to grow into? How can space itself be stretching without an external arena to accommodate it? The answer isn't just some clever wordplay or a gap in our knowledge. It's a description of reality, one that reveals a cosmos far stranger and more elegant than anyone ever thought possible. Get ready to have your concept of space, time, and existence fundamentally challenged. Think of an explosion. It's the first image that pops into our heads when we hear Big Bang. A single, tiny point erupting outwards, flinging shrapnel through a pre-existing, empty room. In this picture, the universe is the shrapnel, the galaxies and stars, and the space it expands into is a vast, passive void. It's a simple, powerful, and deeply intuitive image. And it's completely wrong. Here's the truth, and it's much weirder. The galaxies aren't really flying through space. For the most part, they're just hanging out in their own cosmic neighborhoods. The mind-bending reality is that the space between the galaxies is expanding. The fabric of spacetime itself is stretching, carrying the galaxies along for the ride like they're on a current they can't fight. This isn't a metaphor. It's the literal description of our universe according to Einstein's theory of general relativity and a century of evidence. This one fact changes everything. If space itself is what's expanding, then the question, what is it expanding into, starts to fall apart. It assumes there's an outside, beyond the borders of our spacetime. But if the universe, by its very definition, contains all of space and all of time, then there can't be an outside. Asking what the universe is expanding into is like standing at the North Pole and asking, which way is north? The question itself is built on a false premise. The whole system of direction breaks down at that point. In the same way, the concept of an outside breaks down when we talk about the entirety of existence. The great misconception, the universe as an explosion. Let's break down this explosion idea, because seeing why it's wrong is the key to getting what's right. The image of the Big Bang as a blast in an empty room is what scientists call an embedding diagram. We're trying to picture a 3D process by imagining it inside a bigger space we can look at from the outside. We see the ball of the universe getting bigger inside the room of nothingness. This is just how our brains work. We're built for a 3D world, and our intuition is shaped by it. When a balloon inflates, it pushes against the air in the room. Everything we've ever seen expand has expanded into something. This leads to a bunch of logical sounding but wrong questions. If the Big Bang was an explosion, where did it happen? Where is the center of the universe? Could we fly to the edge and peek into the void beyond? For decades, these questions shaped the popular view of cosmology and fueled sci-fi stories about reaching the end of space. But the universe doesn't follow our everyday rules. General relativity tells a totally different story. The Big Bang wasn't an explosion in space, it was the beginning of space. It happened everywhere, all at once. Every single point in our observable universe today was once right at the site of the Big Bang. There is no center, because the center was everywhere. Any spot in the cosmos can claim to be the center of its own observable universe, seeing all other distant galaxies rushing away from it. This requires a huge shift in perspective. We have to ditch the idea of the universe as an object in a container. The universe is the container. It's not a thing in a place, it's the place itself. The expansion isn't about grabbing new territory from a void. It's about the very nature of distance changing. The ruler we use to measure the cosmos is itself being stretched. 1 billion light-years today is a longer distance than it was in the past. That's the core of cosmic expansion, and it's our first step into the bizarre reality of modern cosmology. The discovery that changed everything. To see how we got to this wild conclusion, let's go back to the early 20th century, a revolutionary time for physics and astronomy. For most of history, the universe was seen as majestic but static. The stars were fixed, an eternal backdrop. Even Albert Einstein believed this at first. When he formulated general relativity in 1915, his own equations described a dynamic universe, one that should be expanding or contracting. He hated this idea so much he added a fudge factor, the cosmological constant, to force his model to be static. He later called it the biggest blunder of his life. The first clue that the universe wasn't static came from a meticulous astronomer named Vesto Slipher in the 1910s. Slipher studied the light from spiral nebulae, fuzzy patches whose nature was a mystery. Using spectroscopy, he split their light into a rainbow of colors. Imprinted on this light are dark lines, like cosmic fingerprints from chemical elements. Slipher noticed something amazing. The lines from most of these nebulae were shifted toward the red end of the spectrum. This redshift is caused by the Doppler effect, the same reason an ambulance siren sounds lower as it moves away. Redshift meant these nebulae were moving away from us, some at millions of miles per hour. The universe was anything but static. But it was Edwin Hubble, in the 1920s with a powerful new telescope, who put it all together. First, he proved that these nebulae weren't gas clouds in our own galaxy. They were incredibly distant, island universes, galaxies in their own right. This discovery expanded the known universe by an astronomical amount overnight. Then, Hubble combined his distance measurements with Slipher's redshift data. In 1929, he found a stunningly simple rule. The farther away a galaxy was, the faster it was moving away from us. This became known as Hubble's law. It wasn't random motion, it was an organized, uniform expansion. This was the first concrete evidence that the universe was expanding. Einstein's original equations were right all along. The static universe was dead, and a dynamic, evolving cosmos was born. The core concept, space itself, is stretching. Hubble's discovery raised a tricky question. If all galaxies are moving away from us, are we the center of the universe? This felt like a huge step backward, an egocentric view most scientists hated. But the truth implied by general relativity was much more elegant. Nobody is at the center, because everywhere is the center. The expansion is happening everywhere equally. To get our heads around this, let's use the most famous analogy in science, the rising raisin bread. Imagine you scatter raisins throughout a loaf of dough and put it in the oven. As the dough bakes, it expands. Pick any raisin and imagine you're standing on it. What do you see? Every other raisin is moving away from you. A nearby raisin moves away slowly, while a distant one moves away quickly, simply because there's more expanding dough between you and it. This perfectly matches Hubble's law. And here's the key. This is true no matter which raisin you stand on. Every raisin sees itself as the center of its own little expanding universe. There is no special center in the dough. The raisins aren't moving through the dough. They're being carried along by the dough's expansion. Now, let's swap back to the cosmos. The galaxies are the raisins, and spacetime is the dough. Galaxies aren't blasting through a static void. Space itself is stretching, and this stretching is what increases the distance between them. This is what's called metric expansion. The metric is just the math that defines distance. The fact that the metric is changing means the very definition of distance is dynamic. Space isn't a passive stage, it's an active player. Another popular analogy is the surface of an inflating balloon with dots drawn on it. As you blow it up, the 2D surface stretches, and every dot moves away from every other dot. The dots aren't crawling across the rubber is expanding underneath them. This balloon analogy is useful, but it has a huge limitation. The 2D surface of the balloon is expanding into our 3D room. This brings us right back to asking, what is our 3D universe expanding into? To make the analogy work, you have to imagine that the balloon's surface is all that exists. There's no air inside and no room outside. The expansion is an intrinsic property of the surface itself. It doesn't need an extra dimension to expand into. This is the big conceptual jump. Our universe's 3 spatial dimensions aren't expanding into a fourth one. The creation of more space is happening intrinsically, everywhere. There is no edge to the universe, just like there's no edge on the surface of a sphere. You can travel on it forever and never fall off. You might end up back where you started, a closed universe, or you might travel forever, a flat or open universe, but you'll never hit a boundary. This is the reality of our cosmos. Possibly infinite, and definitely without an edge to look beyond. The universe has no outside. The idea that the universe is expanding but not into anything is probably the most mind-bending concept in cosmology. Our language fails us here. The word expanding comes loaded with the baggage of our experience, where things always expand relative to some fixed background. But for the universe, there is no external background. The universe is the background. Let's just say it plainly. The universe isn't expanding into anything because, by definition, the universe is everything. It contains all space, all time, all matter, all energy. If there were some void outside the universe, that void would, by definition, be part of the universe. It would be a place, and the universe is all places. And outside is a logical contradiction. Think again about the question, what's north of the North Pole? The question makes grammatical sense, but it's conceptually broken. North, south, east, and west only have meaning on the surface of the Earth. At the North Pole, the concept of north simply stops existing. You can only go south. The question breaks the rules of the system it's trying to operate in. In the same way, asking, what is outside the universe? Or, what came before the Big Bang? Breaks the rules of spacetime. Time and space began with the Big Bang. There was no before for the Big Bang to happen in. Likewise, there is no outside for the universe to expand into. Spacetime isn't expanding within some larger framework. The expansion is the framework. Cosmologists generally consider 2 main possibilities for the universe's overall shape. It could be open or flat, meaning it goes on infinitely in all directions. In this case, the universe has always been infinite, even in the first moments of the Big Bang. It was just an infinitely dense, infinitely hot, infinite space. The expansion just means this infinite space has gotten less dense as the distances between all points have stretched. The other option is that the universe is closed and finite, like the 2D surface of a sphere. In this scenario, if you traveled in a straight line for long enough, you'd end up back where you started. A closed universe is finite, but it still has no edge. The expansion here means its total volume is increasing. But even then, it isn't expanding into anything. Its volume is just growing as an intrinsic change of its own geometry. For a long time, observations of the cosmic microwave background, the afterglow of the Big Bang, suggested our universe is almost perfectly flat, and therefore likely infinite. But whether it's infinite or just unimaginably vast, the conclusion is the same. There is no boundary. There is no edge. There is no outside. Expanding the mystery. Realizing the universe expands into nothing is a huge mental leap, but it's not the end of the story. In fact, it's the gateway to even stranger ideas that are shaking up cosmology right now. For most of the last 30 years, we thought we had the next chapter figured out. In 1998, astronomers studying distant exploding stars, or supernovae, made a shocking discovery that won them a Nobel Prize. They found that the expansion of the universe wasn't slowing down due to gravity, as everyone expected. It was speeding up. This led to the idea of a mysterious force called dark energy, pushing everything apart, making up about 68% of the universe. This became the standard model of cosmology, the lambda CDM model. But science never stands still. And a bombshell finding is challenging everything we thought we knew. A major 2026 study from Yonsei University, published in the * monthly notices of the Royal Astronomical Society, presented strong evidence that this acceleration is an illusion. The study argues that the supernovae we used as standard candles to measure cosmic distances have an age bias. In simple terms, supernovae that exploded in younger galaxies in the early universe appear systematically fainter than those from older galaxies nearby. After correcting for this bias, the picture changes dramatically. The data no longer shows acceleration. Instead, it suggests the universe has recently transitioned into a phase of deceleration. It's slowing down. This doesn't mean dark energy doesn't exist, but it suggests dark energy is not a constant force. It evolves and weakens over time. This might be the key to solving the infamous Hubble tension, a nagging discrepancy between the expansion rate measured locally versus the rate predicted from the early universe. This tension has long hinted that our standard model was incomplete. Now, these new findings might explain why, suggesting a more complex and dynamic dark energy is at play. Other major projects, like the Dark Energy Spectroscopic Instrument, (DESI), have also found tantalizing hints that dark energy is not constant, adding weight to the idea that a paradigm shift in cosmology is underway. So, while the universe may be infinite, our observable universe is not. Because light travels at a finite speed, we can only see out to a cosmic horizon about 13.8 billion light-years away in every direction. There's no reason to think the universe stops there. It's just the limit of what we can currently see. And what's happening within that sphere is suddenly a source of intense debate. This is science in action. We are watching a potential revolution in our understanding of the universe unfold in real time. If these deep dives into the true nature of reality spark your curiosity, make sure you subscribe. We're constantly exploring the latest discoveries, from the frontiers of cosmology to the weirdness of quantum physics. Join our community of explorers as we follow the story wherever it leads. The ultimate fate of the cosmos. The discovery of accelerating expansion gave us a clear, if chilling, prediction for the future. A big freeze, or heat death. In this scenario, the relentless push of dark energy would carry all other galaxies beyond our cosmic horizon, leaving our local group of galaxies as a lonely island in an endless void. Eventually, the stars would die, the black holes would evaporate, and the universe would become a cold, dark, and empty place. But the new evidence that the expansion might be slowing down throws that fate into question. If the Yonsei University findings hold up and dark energy is indeed weakening, the future becomes a complete mystery again. The battle between the outward push of expansion and the inward pull of gravity is back on. This reopens the door to a possibility we had largely dismissed, the Big Crunch. If the deceleration continues, and dark energy keeps weakening, gravity could one day win out. The expansion could halt, reverse, and send the universe collapsing back in on itself, ending in a cataclysmic implosion. On the other hand, there are more exotic theories. What if dark energy's strength were to increase over time? This hypothetical, phantom energy, would lead to a Big Rip, where the expansion becomes so violent it would tear apart galaxies, stars, planets, and eventually, the very atoms that make us up. For the first time in decades, the ultimate fate of everything is genuinely up for grabs. Is our destiny a slow freeze, a fiery crunch, or a violent rip? The answer depends on the true nature of dark energy, a substance that makes up most of our cosmos but which we are only just beginning to understand. We cannot be certain of our ultimate destiny, and that makes the quest for answers more exciting than ever. From a simple observation of reddish galaxies, we've been pulled on an incredible journey to the edge of human comprehension. We've learned that the universe is not an object exploding in a void, but is the void itself, a dynamic, stretching fabric of spacetime. We thought we saw it speeding up, driven by a mysterious dark energy, only to find new evidence that may completely rewrite that story. The answer to the question, what is the universe expanding into? Is, and has always been, nothing. But this nothing is the profound realization that the universe is a self-contained reality, without an outside, an edge, or a center. It's a place far stranger and more magnificent than our intuition could ever prepare us for. And perhaps the most amazing part is that this universe, through a tiny, fleeting arrangement of matter on a small blue planet, has finally started to understand itself. The journey is far from over. The universe is breaking the speed of light. There's a speed limit in our universe, 300,000 kilometers per second. It's the speed of light, and according to Albert Einstein, it's the most fundamental law in physics, a cosmic red light that nothing can ever run. For over a century, this law has been tested and confirmed. It's the bedrock of how we understand reality. And yet, as you're watching this, the universe is breaking its own law on a scale that's almost impossible to comprehend. This isn't happening in some weird, theoretical dimension. It's happening right now, above your head. If you look up into the night sky past the moon, past the planets and stars of our own Milky Way, and out into the vast, crushing emptiness of intergalactic space, you'll find it. Out there, entire galaxies, each with hundreds of billions of stars, are flying away from us faster than the speed of light. How is that possible? How can something so real move at a speed that physics tells us is impossible? Are the laws of physics broken? Was Einstein wrong? The answer is one of the most profound and mind-bending truths in all of science. It's a cosmic loophole, a secret hidden in the very fabric of spacetime. This isn't just a story about speed. It's the story of how the universe actually works, its past, its future, and our tiny place in it all. So, get ready, because we're about to tackle a paradox that changes everything. The law of the land. Einstein's ultimate speed limit. So, to get why the universe seems to be breaking this law, we first need to get the law itself. We've all heard the phrase, nothing can travel faster than the speed of light, but what does that really mean? Why this speed, specifically? The answer is hidden in the most famous equation ever written. E equals mc squared . This equation, which Einstein came up with in 1905, isn't just about unlocking the power of atoms. It's a deep statement about how energy, mass, and speed are all connected. The trick is to think of mass not just as stuff, but as a kind of condensed, resting energy. To make something move, you have to give it kinetic energy. Now, here's where it gets weird. According to Einstein, as you pump more energy into an object to make it go faster, something strange happens. That energy doesn't just increase its speed, some of it starts turning into mass. The object literally gets heavier, more massive the faster it moves. At everyday speeds, like driving on the highway, this change is so tiny it's basically non-existent. But as you get closer to the speed of light, the effect goes wild. Imagine you're pushing a spaceship. At first, it's pretty easy. But as it speeds up, it gets harder and harder to push. It feels heavier. By the time you hit 90% of the speed of light, its mass has more than doubled. To get it to 99%, you'd need to push with 7 times the force. And to reach 999% of light speed, its effective mass balloons to over 223 times its original. You can see where this is going. The closer you get to the speed of light, the more massive the object becomes, and the more energy it takes to speed it up even a tiny bit more. To actually reach the speed of light, the math shows the object's mass would have to become infinite. And to move something with infinite mass, you'd need an infinite amount of energy. Since there's no infinite energy supply in the universe, it's impossible. That's the cosmic speed limit. The only things that can travel at the speed of light are things that have no mass to begin with, like photons, the particles of light itself. For them, it's not just a limit, it's a requirement. A photon has to travel at the speed of light precisely because it's massless. For over 100 years, this law has been a cornerstone of physics. We've confirmed it in giant particle accelerators and we rely on it for our GPS satellites to work correctly. Every experiment has shown it to be true. Einstein's law is as solid as it gets. And that's what makes what we see in the skies so baffling. Because when we look out into the cosmos, we find evidence that seems to shatter this law completely. The scene of the crime, looking at the cosmos. The story of this cosmic crime starts in the 1920s with an astronomer named Edwin Hubble. Back then, most scientists thought the universe was static and that our Milky Way galaxy was pretty much all there was. Other faint, fuzzy patches in the sky, called spiral nebulae, were believed to be just gas clouds inside our own galaxy. Working at the Mount Wilson Observatory, Hubble used the world's most powerful telescope and made a breakthrough in 1923. He spotted a special kind of star, a Cepheid variable, inside the Andromeda Nebula. Thanks to the work of another brilliant astronomer, Henrietta Leavitt, Hubble knew he could use the star's brightness to figure out its distance. His calculations were staggering. Andromeda wasn't a cloud in our galaxy. It was a massive, island universe, full of stars, nearly 1 million light-years away. In that moment, the known universe got a whole lot bigger. But Hubble's greatest discovery was still to come. He started studying dozens of these new galaxies, not just their distance, but also their motion. To do this, he used a technique called spectroscopy. When light from a galaxy passes through a prism, it splits into a spectrum of colors, like a rainbow with a barcode of dark lines. These lines are the chemical fingerprints of the galaxy's stars. Building on the earlier work of Vesto Slipher, Hubble noticed something strange. The spectral lines from most of these galaxies were shifted toward the red end of the spectrum. This redshift is caused by the Doppler effect. You hear the Doppler effect whenever an ambulance passes you. The siren's pitch is high as it approaches and drops as it moves away. The same thing happens with light. If an object is moving away from us, its light waves get stretched, shifting them towards red. What Slipher and Hubble found was that almost every distant galaxy was redshifted. They were all moving away from us. But Hubble took it a step further. He measured both the distance to these galaxies and their redshift, and when he plotted them on a chart, a clear pattern emerged. In 1929, he announced his finding, which became known as Hubble's law. The farther away a galaxy is, the faster it's moving away from us. A galaxy twice as far away recedes twice as fast. The universe wasn't static, it was expanding. This discovery was so profound it even convinced Einstein to abandon his idea of a static universe, which he later called his greatest blunder. But hidden in this law was our paradox. The rate of expansion is described by the Hubble constant. Modern measurements put this value at roughly 70 kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years. So, for every 3.26 million light-years you look farther out, the universe is expanding 70 kilometers per second faster. That might not sound like much, but the universe is a very, very big place. Do the math, and eventually, you reach a distance where the recession speed is predicted to be 300,000 kilometers per second, the speed of light. This is the Hubble sphere, about 14 billion light-years away. And beyond that? The math is crystal clear. Any galaxy farther away must be receding from us faster than the speed of light. This isn't just theory. We've observed galaxies with such extreme redshifts that their recession speed must be faster than light. In fact, some estimates suggest that as many as 97% of the galaxies in our observable universe are now moving away from us faster than light. So here it is. An unbreakable law that nothing with mass can reach light speed, and irrefutable evidence that countless galaxies are doing just that. How can both be true? The cosmic loophole, the revelation. So, how is this possible? Did Einstein get it wrong? Nope. The problem isn't with the law or the evidence. It's with our assumption about what's actually moving. When we hear a galaxy is moving away, we picture it firing up its engines and rocketing through space. But that's not what's happening. The galaxies are, for the most part, just sitting still. They aren't moving through space. The secret, the cosmic loophole, is that space itself is expanding. This is the key that solves the paradox. Einstein's speed limit applies only to objects moving through the fabric of spacetime. It never applied to the expansion of spacetime itself. The universe isn't bound by the speed limit it imposes on everything inside it. Space can expand at any speed it wants. The classic analogy is an inflating balloon. Draw a bunch of dots on a deflated balloon to represent galaxies. As you inflate it, every dot moves away from every other dot. The dots right next to each other move apart slowly, while the dots on the far side of the balloon move apart much faster. The dots aren't walking across the balloon's surface. The rubber itself, the space between them, is stretching. Another good one is a loaf of raisin bread dough rising in an oven. The raisins are galaxies, and the dough is spacetime. As the dough expands, it carries the raisins along for the ride. The raisins aren't swimming through the dough. The dough between them is expanding. This is exactly what's happening in our universe. Individual galaxies have their own motion through space, called peculiar velocity. For example, Andromeda is actually on a collision course with us. But on the largest scales, that's just a tiny wiggle compared to the powerful expansion of space itself, their recessional velocity. This is why Einstein's special relativity isn't violated. That theory deals with objects moving in a static frame of reference. But our universe's reference frame spacetime itself is dynamic. To describe it, you need Einstein's other theory, general relativity, which describes gravity as the stretching and curving of spacetime. And general relativity has no problem with spacetime expanding faster than light. So, when we see a distant galaxy receding faster than light, it's not breaking the speed limit. It's just being carried along by the expansion of space itself. The law isn't broken. It just applies to a different kind of motion. The implications: a universe of horizons. This loophole doesn't just solve a paradox. It reveals a universe with invisible boundaries, separating what we can see from what we can ever hope to reach. Let's go back to that boundary about 14 billion light-years away, the Hubble sphere. Inside this sphere, galaxies recede slower than light. Outside, they recede faster. Now, you might think this means we can't see anything outside the Hubble sphere. How could light from a galaxy moving away faster than light ever reach us? It would be like trying to swim upstream against a current that's too strong. But here again, our intuition leads us astray. We absolutely can and do see galaxies that are currently far outside our Hubble sphere. How? Because when we look at distant objects, we're looking back in time. Think of a galaxy that is now 20 billion light-years away, receding from us faster than light. Billions of years ago, that same galaxy was much closer, well inside our Hubble sphere, moving away slower than light. It sent out a photon back then, which started a long journey toward us. For a while, that photon was on a sort of cosmic treadmill. Even though it was traveling at light speed through its local space, the space between it and us was stretching so fast that it was initially carried away from us. But the Hubble sphere itself is also expanding. As the photon traveled, the Hubble sphere grew, eventually catching up to and overtaking the photon. The moment that happened, the photon found itself in a region of space receding slower than light. The treadmill had slowed down enough for it to finally make progress. From there, it was a clear shot to our telescopes. This is a wild concept. We are getting ancient light from galaxies that, in their present moment, are moving away from us faster than light. We're watching their past as their present reality has already been swept beyond an invisible barrier. This leads to an even more profound boundary. The asterisk cosmic event horizon. This isn't the Hubble sphere. This is the true point of no return. It marks the distance beyond which any event happening right now asterisk will never be seen by us. Light from a galaxy beyond this horizon is carried away by expansion so fast that it will never reach us, no matter how long we wait. It is forever lost to our future. And because the universe's expansion is accelerating, this event horizon is, in a sense, getting closer. Galaxies that are visible today will eventually cross this boundary and, over billions of years, their light will redshift and fade until they vanish from our sky completely. Trillions of years from now, the night sky would be a lonely, empty place. All distant galaxies would have disappeared beyond our event horizon. The only thing left to see would be the few galaxies in our local group, which will have merged into one giant, Milkomeda, super galaxy. Future astronomers living there would look out and see nothing but an endless, starless void, with no way of knowing the true history of the Big Bang that we see today. If your mind is as stretched as spacetime right now, and you want to explore more cosmic mysteries that challenge our reality, this is the perfect time to subscribe. The universe is packed with secrets, from black holes to dark matter, and we explore them all. So hit that subscribe button, because the cosmos is just getting interesting. The driving force, the mystery of dark energy. We've solved the paradox, but it leads to an even deeper mystery. For most of the 20th century, scientists debated the fate of the universe. Would gravity eventually halt the expansion and pull everything back into a big crunch? Or would the expansion just coast forever? Then, in 1998, two teams of astronomers made a discovery that won them the Nobel Prize. They were using distant supernovae as standard candles to measure cosmic distances. They found the most distant supernovae were dimmer, and therefore farther away, than they should have been. The only explanation was that the expansion of the universe isn't slowing down at all. It's speeding up. Something must be pushing spacetime apart, counteracting gravity. Scientists have given this mysterious force a name: dark energy. We have no idea what dark energy is. It seems to be a property of space itself, an anti-gravity, that makes up a staggering 70% of the universe. The normal matter that makes up you, me, and the stars is only about 5%. This accelerating expansion, driven by dark energy, is what's pushing galaxies across our event horizon. But the mystery only deepens. When we try to measure the current expansion rate, the Hubble constant, we run into a problem called the Hubble tension. Different methods give us different answers. Measurements of the early universe, like the afterglow of the Big Bang, give a value of about 67 kilometers per second, (mpc). But measurements of the late universe, using stars and supernovae, give a higher value, around 73 kilometers per second, (mpc). The numbers are close, but their margins of error no longer overlap. It's a major discrepancy that some are calling a crisis in cosmology, suggesting that our standard model of the universe might be missing something fundamental. To try and solve this, scientists are developing new measurement techniques, like using gravitational waves from colliding black holes. The universe is a place of beautiful contradictions, where an unbreakable speed limit can exist side by side with galaxies that appear to be breaking it every second. The solution to this paradox is as elegant as it is profound. Einstein's law governs travel through space, but space itself is expanding, taking galaxies on a ride that has no speed limit at all. This fact reshapes our entire view of the cosmos. It reveals a dynamic, stretching, and accelerating reality, surrounded by invisible horizons that are slowly erasing parts of the universe from our future story. We've learned our universe is driven by forces we've only just begun to name, like the dark energy pushing everything apart. And we've found that even our most basic measurements are filled with tension and mystery. The fact that most of the galaxies we can observe are receding faster than light isn't a sign that physics is broken. It's a sign that the universe is far grander, stranger, and more wonderfully complex than we ever imagined. The ultimate speed limit holds true, it just governs the actors on the stage. It says nothing about the stage itself, which is expanding into a future we can see, but will never reach. Cosmology's biggest lie about the expanding universe. If you ask someone to explain the expanding universe, they'll probably talk about a balloon. You've seen the analogy, maybe you've even used it yourself. It's simple, it's intuitive, and it's taught in classrooms and documentaries all over the world. But what if I told you it's fundamentally wrong? What if this simple picture is hiding the most incredible truth about our cosmos? That this analogy is, in fact, cosmology's biggest lie. It's a lie that conceals a reality so profound it forces us to rethink the very nature of space, time, and existence itself. Because the truth is, galaxies aren't flying apart from each other at all. The very space between them is being created, new, every single second. Today, we're not just popping a balloon. We're blowing the lid off a cosmic misconception to reveal what's really going on in the silent, expanding darkness between the stars. The familiar lie. Let's start with the story we've all been told, the one designed to make the impossibly large feel manageable. It begins with a colorful party balloon. Take a marker, draw a few dots on its deflated surface. Each dot is a galaxy. One is our Milky Way. The others are distant cosmic islands, like Andromeda and Triangulum. Now, start blowing it up. As you puff air into it, the rubber stretches, and something that looks a lot like magic happens. From the perspective of our home dot, the Milky Way, all the other dots begin to move away. And they recede in a very specific way. A dot that was an inch away might move to 2 inches. But a dot that was 3 inches away might now be 6 inches away. The farther the dot, the faster it seems to flee. This perfectly mimics the cornerstone of modern cosmology, discovered by Edwin Hubble in the 1920s. The farther away a galaxy is, the faster it's moving away from us. This relationship is now known as the Hubble-Lemaitre law. The balloon analogy seems to nail it. It gives us a visual, real way to grasp this cosmic rule. It shows expansion happening everywhere. It shows there's no special center of the expansion. From any dot, all the others are rushing away. It feels right. It feels complete. Then there's the second, equally popular analogy, Raisin bread. Imagine a lump of dough with raisins mixed in. As the loaf bakes, the dough rises, expanding in all directions. Every raisin sees every other raisin moving away. Just like the balloon, a faraway raisin will recede much faster than a nearby one because there's more expanding dough between them. Again, it's simple, it's delicious, and it seems to perfectly capture uniform expansion. These analogies are go-to tools for a reason. They take a tricky, mathematical idea, the expansion of a four-dimensional spacetime, and connect it to everyday life. Our brains just aren't wired to visualize the geometry of the entire cosmos. We're used to objects moving through a fixed, pre-existing space. The idea of space itself being a dynamic, stretching thing is deeply weird. The balloon and the raisin bread give us a mental shortcut, a scaffold to hang this idea on. And for most people, that's where the explanation stops. The universe is expanding like a balloon. Simple. Done. But this is where the lie begins. Not a malicious lie, but a lie of oversimplification. A lie that smooths over the cracks in our intuition but, in doing so, blocks us from a staggering, mind-bending reality. Because if you push on these analogies, even a little, they don't just bend. They shatter. And in their breaking, they reveal the real questions that lead to a much deeper and more awe-inspiring truth. The unraveling. The balloon analogy is a beautiful lie, but its power is also its fatal flaw. The problems are hidden in the very things it asks us to ignore. Let's start with the most obvious question, one so simple it feels almost childish. What is the balloon expanding into? When you inflate a balloon, it expands into the room around it. The rubber skin pushes against the air, occupying a volume that was already there. This is the first, and biggest, failure of the analogy. The universe is not expanding into anything. There is no outside. There's no empty void that the cosmos is gradually filling. The very concept of outside is a spatial one, and if the universe contains all of space, then asking what's outside of it is like asking what's north of the North Pole. It's a question that misunderstands the thing it's describing. The expansion of the universe is not an event happening in space, it is a change of space itself. The universe is the whole show, it doesn't need a stage to perform on. Second fatal flaw, the center. Where are you blowing the air from? The center of the balloon. The balloon has a very clear center point. But the universe has no center. The Big Bang was not an explosion at one point in space that flung matter out into a void. That is a huge misconception. The Big Bang happened everywhere. If the universe is infinite, it was always infinite. At the moment of the Big Bang, that entire infinite space was infinitely hot and dense. The Bang was the beginning of the expansion of that space, everywhere, all at once. Every single point in the cosmos can claim to be the center, because from every vantage point, all distant galaxies appear to be receding. You are, right now, at the center of your observable universe. An observer in a galaxy a billion light-years away is at the center of their observable universe. There is no privileged location. Third, let's look closer at those dots we drew. As the balloon inflates, what happens to the ink stains? They stretch out. The dots get bigger. If those dots are galaxies, this implies that galaxies themselves and everything in them should be expanding. Our solar system should be getting bigger. The Earth should be expanding. You should be expanding. But that's obviously not happening. You haven't gotten taller today just because the universe expanded. The reason is that cosmic expansion is a gentle force on local scales. The force of gravity, the electromagnetic forces holding your atoms together, are fantastically, overwhelmingly stronger than this cosmic push. Gravity binds stars into galaxies and planets to their stars. These gravitationally bound systems completely overpower the expansion. They are islands of stability in an expanding cosmic sea. Galaxies aren't expanding on the inside. They are simply being carried away from each other by the expansion of the space between them. The balloon analogy, by stretching the dots, gets this completely wrong. The raisin bread analogy is a little better. It's 3D, and the raisins themselves don't expand. But it still has an edge of crust and it's still expanding into an oven. The universe, as far as we know, has no edge. And so, like the balloon, it ultimately fails. It offers comfort at the price of truth. It's time to toss out these flawed models and face the far stranger, far more magnificent reality they were hiding. The aha moment. The truth revealed. To truly get what's happening, we need to perform a kind of mental surgery. We have to remove the idea of space as a static, empty stage, a fixed grid where the cosmic drama unfolds. This idea is baked into our intuition, but Einstein's theory of general relativity tossed it out a century ago. In its place, he gave us spacetime, a dynamic, bendy fabric, linked to the matter and energy within it. Spacetime isn't the stage, it's one of the actors. It can bend, it can ripple, and, most importantly, it can expand. So, let's try a new analogy. Forget the balloon. Instead, picture an infinite, three-dimensional grid, a vast, invisible lattice stretching out in all directions. This grid is space itself. Now, place the galaxies at various intersections on this grid. And now, watch. The grid itself begins to stretch. The lines that make up the grid, the very fabric of space, are getting longer. The galaxies, just sitting at their intersections, aren't moving through the grid. They aren't firing their engines. They are passive riders, being carried along by the expansion of the grid itself. This is the incredible, mind-bending truth. Galaxies aren't flying through space. Space itself is emerging between them. Let's be crystal clear about what this means. If two galaxies are 1,000,000 light-years apart, it's not that some mysterious force is pushing them apart. It's that, over time, more space appears between them. After a while, there will be more than 1,000,000 light-years worth of space separating them, not because they moved, but because the very ruler of the universe has stretched. This is what physicists call the asterisk metric expansion of space. This new picture immediately solves the problems that shattered our balloon. First, what is it expanding into? Nothing. The grid is infinite. It doesn't need an outside. The stretching is just an intrinsic property of the grid itself. Second, where's the center? There isn't one. Because the entire infinite grid is stretching uniformly, every point sees all other points moving away. This is cosmic democracy. There are no special places. And what about the galaxies themselves? In our new grid analogy, the galaxies are just sitting at the intersections. The intersections move apart, but the objects themselves don't stretch. A galaxy's size is determined by its own gravity, which easily holds it together against the gentle, large-scale stretching of space. So, our solar system doesn't expand, and you don't expand. The space within our galaxy is locked down by gravity. But the vast, empty voids between galaxy clusters? That space is expanding, carrying those clusters along for the ride. This also explains Hubble's law perfectly. Why do more distant galaxies recede faster? Imagine 3 galaxies in a line on our grid: A, B, and C. The space between A and B is 1 unit. The space between B and C is also 1 unit. Now, let space expand, so each unit doubles in length. From his perspective, galaxy B, once 1 unit away, is now 2 units away. It receded by 1 unit of distance. But galaxy C, which started 2 units away, is now 4 units away. It receded by 2 units of distance in the same amount of time. It appears to be moving twice as fast. It's not that C has a higher velocity through space. It's that there was twice as much expanding space between A and C to begin with. This is why some distant galaxies can recede from us faster than the speed of light. It doesn't violate relativity, because nothing is moving through space faster than light. It is space itself that's expanding, and there's no speed limit on that. This is the aha moment. The universe isn't a bomb that exploded. It is a continuously rising loaf of bread, but one that is infinite in size, has no crust, and whose dough is the very fabric of reality. This idea of a stretching fabric of reality sounds like science fiction, but it is one of the most rigorously tested concepts in all of science. The evidence is written across the entire sky. The primary piece of evidence is cosmological redshift. When light from a distant galaxy travels to us, the space it journeys through is continuously expanding. This stretching of space has a direct effect on the light wave itself. It stretches the wavelength. Longer wavelengths are redder, so we call this redshift. It's not the classic Doppler effect, like a siren changing pitch. The galaxy isn't just flying away. It's that the light wave is stretched by the expansion of space itself as it travels. The longer it travels, the more it gets stretched. This is exactly what Hubble saw. The farther away a galaxy is, the more its light is redshifted. The redshift is a direct measurement of how much the universe has expanded since that light began its journey. The second towering piece of evidence is the cosmic microwave background, CMB**. This is the oldest light in the universe, a faint afterglow from the Big Bang, released about 380,000 years after it all began. Back then, this light was incredibly hot and energetic. But over the last 13.8 billion years, its wavelength has been stretched by the expansion of space by a factor of over 1,000, all the way down to the microwave part of the spectrum. When we look at the sky with microwave telescopes, we see this ancient, almost perfectly uniform light coming from every direction, a stunning confirmation of a universe that started hot and dense and has been expanding and cooling ever since. Then, in 1998, cosmology was turned on its head. Astronomers were using special exploding stars type Ia supernovae as standard candles to measure the expansion rate precisely. They expected to find that the expansion was slowing down, pulled back by gravity. They found the exact opposite. The distant supernovae were even fainter than they should have been, meaning they were farther away than predicted. The only explanation was that the expansion of the universe was not slowing down, but accelerating. This was a shocking, Nobel Prize-winning discovery. Something was actively pushing space apart, overpowering gravity on the largest scales. This mysterious something was given a name: dark energy. According to our best models, dark energy makes up about 70% of everything in the universe. It appears to be a property of space itself. As space expands, more space is created, and thus more dark energy, which causes the expansion to accelerate even faster. And this story got a wild new chapter recently. Instruments like the Dark Energy Spectroscopic Instrument, (DESI), have been making the most detailed 3D maps of the universe ever. When scientists combined DESI's data with other cosmic observations, they found mounting indications that the influence of dark energy might actually be weakening over time. It's not a slam dunk yet, but it's the first real hint in over 20 years that dark energy isn't a constant. If it holds up, it could change everything we think we know about the ultimate fate of the universe. We just threw out the textbook analogy for the expanding universe and replaced it with a truth that is infinitely more fascinating. If you love getting to the real story behind the science, that's what we do here. So hit that subscribe button and join us as we keep digging for the truth together. Accepting that space itself is expanding and accelerating isn't just a minor correction. It's a fundamental shift in our perception of reality, with consequences that are profound, strange, and beautiful. It solves puzzles like, does the universe have an edge? Probably not. Our best measurements suggest the universe is flat, and a flat universe likely extends infinitely in all directions. Even if it were finite and closed, like the 3D surface of a 4D sphere, it would still have no edge. You could just travel in one direction and end up back where you started. You can never stand at the precipice of the cosmos and look out. There is no out. But this leads to a stunning consequence: the observable universe. While the universe itself may be infinite, the part of it we can see is finite. This isn't a wall in space, but a boundary in time. The universe is 13.8 billion years old, so we can only see things whose light has had 13.8 billion years to reach us. This creates a sphere around us, our cosmic horizon, marking the edge of what we can ever see. And here's the twist. Because space is expanding, the objects that emitted that light billions of years ago are now much, much farther away today. The edge of our observable universe is about 46.5 billion light-years from us. And because the expansion is accelerating, there are galaxies we can see today that have already been carried away from us so fast that they've crossed a different kind of boundary: the cosmic event horizon. We are seeing their past, but their present is already causally disconnected from us forever. Any light they emit now will never reach us, because the space between us is expanding faster than light can travel across it. We are watching them fade away as they are carried off by the swelling tide of spacetime. This leads to the ultimate question: what is the fate of the universe? If dark energy is constant, the Standard Model predicts a lonely future. As acceleration continues, all galaxies not gravitationally bound to us will eventually cross that event horizon and vanish from our sky. Imagine an astronomer trillions of years from now. Looking out, they would see only the few galaxies in our merged local group. Beyond that? Nothing. An endless, empty blackness. They would have no evidence of other galaxies, no sign of cosmic expansion, no hint of a Big Bang. The evidence of our grand, dynamic cosmos would have been literally expanded away. This scenario is known as the big freeze or heat death. Now, if those recent hints about dark energy weakening are true, this lonely fate might change. But for now, the big freeze remains the most likely end to our cosmic story. The lie of the balloon gave us a simple pop. The truth gives us a possible eternity of silent, cold, accelerating darkness. So, we return to the simple, intuitive, and fundamentally wrong image of an expanding balloon. We called it a lie, not out of malice, but because it tried to package a reality too vast for our minds into a neat, tidy box. But the universe has never fit neatly into our boxes. The moment we let go of the balloon, the real cosmos is revealed. It's a universe without a center and without an edge. A universe where the Big Bang wasn't an explosion in one spot, but an event that happened everywhere, in a space that was likely already infinite. A universe where galaxies are passive islands being carried apart by the very fabric of reality, a fabric that is constantly being woven into existence between them. The biggest lie about the expanding universe wasn't just an oversimplification, it was a failure of imagination. It replaced a concept that is dynamic, active, and mind-altering with one that is small and contained. The truth that the stage of our existence is a living, growing entity is far grander. It transforms the darkness between the stars from a void into a wellspring of new space. We live in a special time, an era where we can still see the evidence of our cosmic origins, before it all expands away beyond our reach. We are privileged witnesses to the grand narrative of the cosmos. And understanding the truth behind the lie allows us to appreciate that narrative in its full, staggering glory. The next time you look up at the night sky, don't picture a balloon. Picture an infinite, invisible grid, stretching in every direction. And know that with every second that passes, that grid is stretching, creating more space, more distance, more universe. You are not just living in the expansion, you are part of it. And that is a truth far more wonderful than any lie. Why the universe is expanding into absolutely nothing. Think about the word expanding. What comes to mind? A balloon inflating in a room, a city sprawling into the countryside, a puddle spreading across the floor. For our brains, expansion means one thing moving into something else. There's always a pre-existing space that's being filled or pushed aside. It's how we experience the world. So, what if I told you the entire universe is expanding into absolutely nothing? No outside. No void. No bigger room for it to fill. It sounds impossible, doesn't it? It feels like a riddle that breaks the basic rules of logic. And honestly, it's a concept that pushes our minds to their breaking point. But by the end of this, not only will you get how it works, you'll see it's the only way it could work. And the key to unlocking this whole cosmic mystery? It's a simple balloon. The very thing our intuition uses to get it wrong can, if you look at it just right, show us the truth about the cosmos. Stick with me, because this is one of those ideas that might just reshape how you picture reality. The paradox of expansion and why common sense fails. Let's be honest, the phrase, "the universe is expanding," creates an instant mental picture. We imagine the Big Bang as a kind of cosmic firework, a ball of light and matter exploding outwards. In that picture, there's a clear edge, a frontier pushing into a huge, dark, empty space. It's a natural image, because it's based on every explosion we've ever seen. So when a cosmologist says the universe is expanding, the first question we ask is, into what? It's just logical. If it's getting bigger, it must be growing into something. A bigger, emptier void? Another dimension? But how can anything expand into nothing? Nothing is. Well, nothing. It has no dimensions, no properties, no existence. The very idea of occupying non-existence is a dead end. It's like asking what's north of the North Pole. The question itself doesn't make sense because it's based on a flawed starting point. And you're in good company if this feels like a paradox. It stumped some of the greatest minds for a while. It feels like you need an outside to have an inside. Our entire language is built on these pairs, up and down, left and right, inside and out. We're wired for a three-dimensional world, and our thinking is shaped by its rules. But the universe as a whole doesn't play by the same rules as our living rooms. To start solving this, we have to do something tricky. We have to let go of the idea of the universe as an object in a place. The universe is the place. It's not a collection of galaxies sitting in an empty box. The universe is the box and everything in it, all space, all time, all matter and energy. By definition, there can't be anything outside of it, because if there were, we'd just call that part of the universe, too. This isn't just a word game. It's a description of reality that came from hard evidence that started painting a completely new picture of the cosmos about a century ago, all thanks to one man and a game-changing telescope. To get how we know the universe expands into nothing, we first have to understand how we found out it was expanding at all. And for that, we need to go back to the 1920s. The historical context: Hubble's earth-shattering discovery. For most of history, the universe was seen as this grand, static, unchanging stage. Planets might wander, a comet might show up, but the stars were called fixed stars for a reason. They were considered permanent. This idea was so powerful that even Albert Einstein bought into it. When he developed his theory of general relativity in 1915, his own math was telling him the universe should be dynamic, either growing or shrinking. He thought his calculations must be wrong, so he added a fudge factor he called the cosmological constant, just to force his equations to produce a stable, static universe. He'd later call it his greatest blunder, because the universe wasn't static. And the proof came from the cold, clear nights on Mount Wilson in California. There, an astronomer named Edwin Hubble was tackling a huge debate. What were those spiral nebulae, the faint, fuzzy patches of light scattered between the stars? Were they just gas clouds inside our own Milky Way, as many prominent astronomers believed? Or were they entire, island universes? Galaxies just like ours, but an unimaginable distance away? The only way to know was to measure their distance. Hubble pointed his telescope at the Andromeda Nebula and, in 1923, found what he was looking for: a special type of star called a Cepheid variable. Thanks to the work of another incredible astronomer, Henrietta Leavitt, it was known that the speed at which these stars pulsed was directly linked to their true brightness. By comparing how bright a Cepheid actually was to how dim it appeared, Hubble could calculate its distance. The result was a bombshell. His calculations put Andromeda at nearly 1,000,000 light-years away, vastly beyond the edge of the Milky Way. Today, with even better tools, we know it's even farther, about 2.5 million light-years. These weren't little clouds. They were galaxies. Sprawling cities of billions of stars. In an instant, the known universe got about 100 times bigger. But that wasn't even his biggest discovery. Hubble kept going, measuring not just the distance to these galaxies, but also their speed. He used the work of Vesto Slipher, who had spent years analyzing the light from these nebulae and found something odd. The light from almost all of them was redshifted. Think of an ambulance siren. As it comes toward you, the sound waves get squished, and the pitch gets higher. As it moves away, the waves stretch out, and the pitch gets lower. Light does the same thing. If an object is moving away from you, the light waves it emits get stretched. This stretching shifts the light toward the red end of the spectrum. That's redshift. Slipher saw that nearly every galaxy was redshifted. They were all moving away from us. Hubble put the two pieces together: his distances and Slipher's speeds. When he plotted them on a graph, the pattern was undeniable. The farther away a galaxy was, the faster it was moving away from us. This became known as Hubble's law. This wasn't random movement, like bees buzzing in a hive. This was an organized retreat. Every galaxy was running away from every other galaxy. The only explanation was that the very fabric of the universe itself was expanding. He published his findings in 1929, and our view of the cosmos was changed forever. The static, eternal universe was gone, replaced by a dynamic one that had a beginning. But this led right back to that nagging question. If everything is flying apart, what is it all flying apart into? The answer wasn't out there in the dark. It was in refining that simple analogy we all think of: the balloon. The aha moment. The analogy that changes everything. Okay, this is the part that can feel like a brain bender, but stick with me, because this is the aha moment. It all comes down to a balloon. Now, when you first picture the expanding universe as a balloon, you probably imagine blowing up a balloon in your living room. The balloon is the universe, and the room is the nothing it expands into. That's the firework model, and it's the wrong way to think about it because it keeps that idea of an outside. So, let's try it again. But this time, you have to change your perspective. You are a tiny, two-dimensional creature living on the surface of the balloon. That surface is your entire universe. You have no idea what a third dimension is. You can't look up, off the surface, or down, into the center. Your whole reality is just this curved, stretchy sheet of rubber. Let's draw some dots on that surface. Each dot is a galaxy. You're standing on one of them, the Milky Way dot. Now, someone starts inflating the balloon. What do you see? From your spot on the Milky Way dot, you notice something amazing. Every other dot is moving away from you. A dot that was an inch away is now 2 inches away. A dot that was 5 inches away is now 10 inches away. And you see a clear pattern. The farther away a dot is, the faster it seems to be moving away. That's a perfect match for Hubble's law. But here's the kicker. Let's say you instantly teleport to a different dot on the far side of the balloon. What do you see now? The exact same thing. From your new spot, every other dot including the one you just left is moving away from you. From the surface of the balloon, there is no center of the expansion. Every point looks like the center. There's no special spot. And there's no edge. You could walk in a straight line forever and you'd never fall off. You'd just loop around and end up right back where you started, just like walking around the Earth. Your universe is finite, but it has no boundary. And here's the most important part. Are the dots the galaxies actually moving across the rubber? No. They're sitting still on the surface. It's the rubber itself, the very fabric of your 2D space, that is stretching. The expansion isn't galaxies flying through space. It's the expansion of space between the galaxies. They're just along for the ride. So for the final leap, when the balloon inflates, does its 2D surface expand into anything? From your perspective as a 2D creature, no. The expansion is completely self-contained on the surface. The surface just gets bigger. It doesn't need a 3D room to expand into for its own 2D expansion to be real. That's our universe. Our 3-dimensional space is like that 2-dimensional surface. And just as the 2D surface can be curved through a third dimension you can't see, our 3D space might be curved through a higher, fourth spatial dimension we can't perceive. Or, it might be flat, like an infinite rubber sheet stretching out forever. But even in that infinite case, the rule still holds. If you stretch the entire sheet everywhere at once, every point on it moves away from every other point. This is what metric expansion means. It's an expansion of space itself. And it shows that the question, what is the universe expanding into, is based on a flawed assumption. It's the wrong question to ask. The physics of an expanding spacetime. The balloon is a great analogy, but the real science behind this comes from one of the pillars of modern physics, Einstein's general theory of relativity. Before Einstein, Newton saw gravity as an invisible rope pulling things toward each other on a fixed, unchanging stage of space. But Einstein's idea was far wilder. He said space and time aren't a static backdrop. They're woven together into a single, dynamic fabric called spacetime. And gravity isn't a force. Gravity is what we feel when we move through spacetime that has been curved by mass and energy. As physicist John Wheeler put it, spacetime tells matter how to move. Matter tells spacetime how to curve. Think of a bowling ball on a trampoline. It makes a big dent. If you roll a marble nearby, it doesn't get pulled by the bowling ball. It just follows the curve in the trampoline's surface. That's Einstein's gravity. When scientists applied these equations to the whole universe, they found that the math didn't want a static universe. The equations naturally described a spacetime that was either expanding or contracting. Hubble's discovery was the stunning proof that the math had been right all along. The solution to Einstein's equations that describes our universe is called the FLRW metric. It's basically the master equation for the universe's geometry, and it's built on an idea called the cosmological principle. This principle says that on the largest scales, the universe is both homogeneous, it's pretty much the same everywhere, and isotropic, it looks the same in every direction. This is the scientific way of saying there is no special place in the universe. There's no center and no edge. If the universe is the same everywhere and in every direction, then any point can be considered the center, which means no point is the center. Just like on the balloon. The FLRW metric contains a variable called the scale factor. You can think of it as a number that describes the size of space. When that number gets bigger, the universe is expanding. The distance between any two faraway galaxies is directly tied to this scale factor. So when we say the universe is expanding, what we're really saying is that the scale factor is increasing. Galaxies aren't like cars speeding down a highway. They're more like fence posts in a field of rubber that's being stretched. The space between them is what's growing. This leads to a seriously weird consequence. If you look far enough away, the expansion of space is so great that some galaxies are receding from us faster than the speed of light. Now, wait a minute. Didn't Einstein say nothing can go faster than light? Yes, but that rule applies to things moving through space. You can't travel from point A to point B faster than light. But that's not what's happening here. The galaxy isn't rocketing through space at impossible speeds. The space between us and it is expanding so fast that the total distance is growing faster than a beam of light could cross it. The galaxy is just being carried by the current. No laws of physics are broken, but it's a bizarre outcome of space itself expanding. So, the paradox is solved. The universe doesn't need to expand into anything because it's the expansion of everything. Alright, that's a lot to take in. We've gone from a simple paradox to the mind-bending math of spacetime itself. We've seen how the stretching of the universe is a core prediction of our best theory of gravity. But the story gets even stranger. The expansion isn't just happening, it's speeding up. And the reason why is one of the biggest mysteries in all of science. The modern twist, dark energy and the accelerating cosmos. For decades after Hubble, the big question was, will the expansion go on forever, or will gravity eventually win, stop the expansion, and pull everything back together in a big crunch? The fate of the universe depended on this cosmic tug-of-war. To find out who was winning, two teams of astronomers in the late 1990s set out to measure the expansion rate deep in the past. They used Type Ia supernovae, a kind of exploding star, as their measuring sticks. These supernovae are fantastic, standard candles, because they always explode with roughly the same peak brightness. If you know how bright something really is, you can tell how far away it is just by seeing how dim it looks. The teams looked at supernovae in incredibly distant galaxies, seeing the universe as it was billions of years ago. They expected to find that the expansion had slowed down over time. But they found the exact opposite. The distant supernovae were dimmer and therefore farther away than they should have been. The only way that could happen is if the expansion of the universe had been speeding up for the last several billion years. This discovery was a complete shock. It won its leaders the Nobel Prize in 2011 and showed there was a third player in the cosmic tug-of-war, a mysterious, repulsive force pushing spacetime apart. Scientists gave it a name, dark energy. We still don't really know what dark energy is. The top theory is that it's a property of the vacuum of space itself, an energy of empty space, that Einstein once proposed and then threw away. In this view, as space expands, more space is created, which means more dark energy, which pushes space to expand even faster. It's a runaway feedback loop. Today, our best estimates say the universe is about 5% normal matter, stars, planets, 27% dark matter, an invisible substance we only detect via gravity, and a whopping 68% dark energy. This mysterious energy is now the dominant force in the cosmos, and it's hitting the gas pedal on expansion. This leads to some wild possibilities for the end of the universe. If dark energy keeps this up, we're likely headed for a big freeze. The accelerating expansion will push all other galaxy groups away from us so fast they will eventually disappear from view, their light no longer able to reach us. Our sky will grow dark. Over trillions of years, stars will burn out, and the universe will become a vast, cold, and empty void. A more dramatic, though speculative, fate is the Big Rip. In this scenario, dark energy gets stronger over time, becoming so powerful it would eventually tear apart galaxies, then solar systems, planets, and in the final moments, atoms themselves. But the final chapter isn't written yet. There is still a chance for a big crunch, a future where the expansion reverses. This would require dark energy to weaken over time. Incredibly, recent data from projects like the Dark Energy Spectroscopic Instrument, DESI, has given us some tantalizing hints that dark energy might not be constant after all. The cosmic acceleration might be slowing down. This has reignited a huge debate in cosmology and keeps all possibilities on the table. So, we come back to where we started. Our universe, expanding into nothing. We've seen that it's not a paradox, but a natural result of the way spacetime works. The universe doesn't expand into anything because there's no outside to expand into. It is the intrinsic stretching of reality itself, a process first hinted at by Einstein's math and proven by Hubble's telescope. We're living on the surface of this expanding cosmos, where every spot looks like the center and there's no edge to fall from. And we've learned this expansion is speeding up, driven by a mysterious dark energy that is now writing the next chapter of the cosmic story, a future that could be cold and lonely, violently final, or something else entirely. Grappling with this idea forces us to loosen our grip on common sense and accept a reality that is far stranger, and far more magnificent, than our everyday lives prepare us for. The universe isn't a firework in a dark room. It is the room itself, growing larger in all directions, creating more space as it goes. It expands into nothing, and in doing so, creates everything. The uncomfortable truth at the edge of reality. What is the universe expanding into? It's a simple question. It feels natural, almost necessary to ask. And it leads to an answer so profound, so counterintuitive, that our brains aren't truly built to handle it. We instinctively picture an edge, a final frontier, a boundary with something else on the other side. A void, maybe. Another dimension. But what if the most uncomfortable truth, the one waiting for us at the perceived edge of reality, is that there is no other side? What if the shocking realization isn't what the universe is expanding into, but that there is no into at all? This isn't a riddle. It's the astonishing reality described by modern cosmology. And to understand it is to rewire your entire perception of existence. The problem of intuition. Our entire human experience is a story of boundaries. From birth, we understand the world through containers. The walls of a room. The shores of an ocean. The skin that holds us together. Everything has a limit, an inside and an outside. When we see something expand, like a firework or ripples in a pond, it always expands into a pre-existing space. This is the logic hardwired into our neural circuitry. Our ancestors didn't need to ponder an edgeless existence to survive. They needed to know the boundaries of their territory. So, when we learn the universe is expanding, our minds default to a familiar mental model. We picture the Big Bang as an explosion at a single point in an infinite, black, empty room. The universe is the shrapnel from that blast, flying outwards into the emptiness. It's a powerful and intuitive image. It's also completely wrong. This question, what is the universe expanding into, is a symptom of this flawed model. Early philosophers and astronomers wrestled with it. Aristotle figured the universe had to be finite, held in a great celestial sphere, because an infinite expanse was illogical. For centuries, this was the prevailing wisdom. The cosmos was a grand, but contained, system. This mental trap feels like common sense. But in cosmology, common sense is often the first casualty. To break free, we have to dismantle the idea of the Big Bang as an explosion in space. The Big Bang wasn't an event that happened in a void. It was the beginning of space itself. It didn't happen at a single point in a dark room. It happened everywhere, all at once. Every single point in the universe we see today was, at that first moment, the same point. Yeah, this is weird. Your brain is right to be confused. We're trying to visualize something with no parallel in our daily lives. There is no analogy for the beginning of everything. But sticking with this strange idea is the first step. It helps us understand the expansion not as a journey through space, but as the expansion of space. Let's hold on to that thought. Space itself is expanding. It's a radical idea that came from one of the greatest upheavals in scientific history, one that began with a man who initially disliked the very concept. His name was Albert Einstein, and his theory of gravity would accidentally unlock the secret of cosmic expansion, forcing him to confront a universe far stranger than even he had imagined. The turning point. A fabric in motion. For most of history, space was just an empty, invisible backdrop. The absolute and unchanging grid where the cosmic drama unfolded. This was Isaac Newton's universe, and it reigned for over 200 years. It was elegant, powerful, and astonishingly accurate. Then, in the early 20th century, Albert Einstein demolished it. His breakthrough began with a thought experiment. What's it like to fall? He realized that in freefall, you don't feel your own weight. This principle of equivalence led him to a revolutionary vision of gravity. Gravity, he proposed, wasn't a force pulling on things. It was a feature of space itself. This is the core of his general theory of relativity, published in 1915. Einstein wove space and time together into a single, dynamic, four-dimensional fabric, spacetime. And this fabric isn't passive. It can be bent, warped, and curved by mass and energy. As the physicist John Archibald Wheeler famously put it, spacetime tells matter how to move. Matter tells spacetime how to curve. Think of a bowling ball on a rubber sheet. It creates a dimple. A marble rolled nearby will follow that curve. That, Einstein said, is gravity. The Earth isn't being pulled by the sun. It's following the straightest possible path through the curved spacetime the sun creates. This was a mind-bending shift. Space was no longer a stage, it was a performer. But when Einstein applied his equations to the whole universe, he found something that troubled him. They predicted that a universe full of matter couldn't be static. Gravity should cause the entire fabric of spacetime to collapse. Since the prevailing view was of a static, eternal universe, Einstein added a fudge factor to his equations, the cosmological constant. It acted as a repulsive force to perfectly balance gravity. He later called this his greatest blunder. Because while Einstein was trying to hold the universe still, astronomers were finding evidence that it was anything but. The story shifts to a mountaintop in California and an astronomer named Edwin Hubble. In the 1920s, Hubble was measuring distances to faint smudges of light called spiral nebulae. He made a shocking discovery. They weren't gas clouds in our own Milky Way. They were entire galaxies, millions of light years away. The universe was vastly larger than anyone knew. But that wasn't all. Working with earlier data from Vesto Slipher, Hubble noticed the light from these distant galaxies was shifted toward the red end of the spectrum. This redshift is a cosmic Doppler effect. Just as an ambulance siren's pitch drops as it moves away, light from an object moving away from us stretches to longer, redder wavelengths. What Hubble found was staggering. Almost every galaxy was redshifted. And he discovered a simple relationship, now called the Hubble-Lemaitre law. The farther away a galaxy is, the faster it's receding. This was the proof Einstein had dismissed. The universe wasn't static, it was expanding. When Einstein heard of Hubble's findings, he recognized his mistake, abandoned his cosmological constant, and realized his original equations had been pointing to a dynamic, evolving universe all along. But there are wrinkles in this story. Today, there's a major debate in cosmology known as the Hubble tension. Measurements of the expansion rate using early universe data, like the afterglow of the Big Bang, give one value, while measurements using late universe objects, like supernovae, give a slightly different, faster value. This stubborn discrepancy suggests our picture of the cosmos might still be missing a piece of the puzzle. The revelation: there is no outside. Hubble's discovery seems to put us at the center of a cosmic explosion. But that's an illusion. The key is that it's not galaxies flying through space, but space itself expanding between them. Cosmologists use a classic analogy: raisin bread. Imagine a lump of dough, spacetime, with raisins, galaxies, scattered in it. As the dough bakes and rises, every raisin moves away from every other raisin. From the perspective of any raisin, all the others are receding, and the farther ones recede faster. This is exactly what Hubble's law describes. No raisin is the center. The expansion is happening everywhere. Another analogy is an expanding balloon. Imagine dots drawn on the balloon's surface. As you inflate it, the 2D surface stretches, and every dot moves away from every other dot. There is no center asterisk on the surface of the balloon. The center is inside, in a third dimension the 2D dot creatures can't access. Now, this is where you have to be careful. The raisin bread expands in an oven. The balloon expands in a room. This reinforces our bad intuition. For the real universe, there is no oven. There is no room. The expansion is the creation of new space, everywhere, between galaxies. There is no higher dimensional, outside, that it's expanding into. So what about the edge? Surely there must be a boundary where it all stops. Here, we face two main possibilities for the universe's overall geometry. Our best measurements suggest the universe is flat on the largest scales, meaning standard geometry applies. The simplest model for a flat universe is an infinite one. If the universe is infinite, the question of an edge is meaningless. An infinite thing doesn't have an edge. It just gets more infinite. But what if the universe is finite? This is where our brains really struggle. It's mathematically possible for something to be finite yet have no boundary. Think of the 2D surface of the balloon again. You can travel across it forever and never fall off an edge. You just loop back to where you started. Now, imagine a 3D version of that, a universe finite in volume, where if you travel in a straight line long enough, you end up right back where you started, without ever hitting a wall. In either a finite or infinite universe, the conclusion is the same. There is no edge. There is no outside. The question, what is it expanding into, is based on a false premise. The universe contains all of space and time. By definition, there can be nothing outside of it. This is it. This is the uncomfortable truth. The answer isn't some mystical void, but a conclusion that is both simple and profoundly alien to our minds. There is nothing outside the universe. The very concept of outside is a spatial term that loses its meaning when you're talking about all of space itself. The uncomfortable conclusion. A brain built for boundaries. Let's pause. The universe isn't expanding into anything. It's just expanding. Why does that feel so weird? The answer is in our heads. Our brains are masterpieces of evolution, tuned for survival on a small planet. We evolved in a world of edges and containers. Inside versus outside. This logic is a foundational part of our perception. When cosmology tells us no such cosmic limit exists, it feels like a violation of logic itself. This discomfort is the feeling of your mind brushing up against its own evolutionary limits. It's like trying to run software on hardware it was never designed for. This is complicated by the observable universe. While the whole universe may be infinite, the part we can see is finite. Because light travels at a finite speed and the universe is about 13.8 billion years old, there's a horizon beyond which we cannot see. Light from galaxies beyond this cosmic horizon simply hasn't had enough time to reach us. That horizon is currently about 46.5 billion light years away in every direction. It's tempting to call this the edge, but it's an informational boundary, not a physical one. An observer in a galaxy near our horizon would have their own observable universe, including regions we can't see. Everyone, everywhere, appears to be at the center of their own observable universe. This is a core idea in cosmology known as the cosmological principle. On large scales, the universe is the same everywhere and in every direction. So, the edge we can point to isn't a true edge of reality. It's a personal horizon. Beyond it, the universe almost certainly stretches on, filled with more galaxies, maybe infinitely. And all of it, the seen and the unseen, is expanding. The uncomfortable truth, then, is that our own minds are the source of the confusion. We're trying to impose a human-scale concept of outside onto a system where it's meaningless. It requires a kind of intellectual surrender, accepting that the universe doesn't have to conform to the logic that governs our immediate environment. The universe isn't a box. There is no outside to look in from. There is only the universe. The journey to the edge of reality doesn't end with a tidy answer. It ends with a shift in perspective. The question, what is the universe expanding into, is a trick question, built on a misunderstanding, like asking what's north of the North Pole. The answer that there is no into can feel unsettling. It removes the final boundary. But it's also magnificent. It means the universe's existence. The expansion isn't a journey to somewhere else. It's the dynamic unfolding of spacetime itself, happening right here, right now. And the story is still evolving. The simple model of accelerating expansion isn't settled fact. As of early 2026, data from the Dark Energy Survey suggests that the standard lambda CDM model of the cosmos might need revising. There's a growing discrepancy in how matter clumps together, hinting that the nature of dark energy could be more complex than we thought. Some physicists now even entertain a radical alternative. The expansion might not go on forever. A new analysis suggests the universe could reach a maximum size in about 11 billion years and then collapse in on itself in a big crunch, some 20 billion years from now. This uncomfortable truth is a testament to the grandeur and bizarre nature of our cosmos. It's a humbling reminder that our experience is just one limited slice of a much larger, stranger reality. The universe isn't playing by our rules. And realizing that is one of the most profound and awe-inspiring insights science has ever offered.